Please subscribe to support the channel. What is the strongest object in the universe? When you hear that question, your mind might jump to black holes, the ultimate cosmic devourers with gravity so strong that not even light can escape. Or maybe you'd think of neutron stars, those ultra-dense remnants of supernovae that compact the mass of our sun into a sphere barely a dozen miles wide. Some might even suggest entire galaxies, vast collections of hundreds of billions of stars bound together by dark matter and gravity. But what if I told you that the answer is something far stranger? Something that doesn't fit our usual definition of strength, and yet, by all accounts, has proven itself to be one of the most resilient survivors in the hostile environment of the cosmos? That something is known as the G2 cloud. At first glance, calling a gas cloud the strongest object in the universe might sound absurd. A gas cloud is supposed to be delicate, ephemeral, the kind of thing that should get ripped apart instantly by the titanic forces near a supermassive black hole. But the G2 cloud defies this expectation. It has done something that shocked astronomers, something that turned our understanding of cosmic destruction upside down. It survived a close encounter with Sagittarius A, the supermassive black hole at the center of our galaxy. Now let's unpack this carefully. Strength, in the traditional sense, often means resistance to force. A diamond is strong because it resists scratching. A neutron star is strong because it resists collapse with pressures unimaginable on Earth. But the G2 cloud demonstrates a different kind of strength, survival against the odds. By enduring one of the most hostile gravitational encounters possible, it proved itself to be more than just a puff of gas. Its existence challenges our ideas of what fragile and strong really mean in the cosmic context. And that's what makes the G2 cloud so fascinating. When it was first observed, scientists were convinced it was doomed. Predictions of its demise filled astronomy journals and fueled global anticipation. Telescopes were turned toward the galactic center to witness the spectacle of a gas cloud being shredded and consumed by a black hole's unstoppable gravity. It was supposed to be a fireworks show of cosmic proportions. Instead, the universe threw us a curveball. The cloud came through battered, perhaps altered, but undeniably intact. That survival is what earns G2 its place as a candidate for the strongest object in the universe. Not because it exerts the most power, not because it crushes other objects with gravity, but because it withstood an encounter with one of the greatest destructive forces we know, and emerged with its identity preserved. That, in itself, is a kind of cosmic power. So when we ask again, what is the strongest object in the universe? We realize that strength doesn't always look like brute force. Sometimes, strength is endurance. Sometimes, it is resilience. And sometimes, in the heart of our galaxy, strength takes the form of a mysterious, glowing cloud of gas that refused to be destroyed. To truly appreciate the mystery and significance of the G2 cloud, we first need to set the stage by looking at where this remarkable object resides. Imagine the Milky Way, our home galaxy. To us on Earth, it appears as a faint, hazy band stretching across the night sky. But in reality, it's a sprawling disk of stars, planets, nebulae, and dark matter that measures over 100,000 light-years across. At its heart lies something extraordinary, a gravitational monster known as Sagittarius A, a supermassive black hole with a mass equivalent to more than 4 million suns. This black hole is invisible to the naked eye, but it makes its presence known through the motion of the stars that orbit close to it and through the radiation emitted by the swirling gas and dust spiraling toward its event horizon. Sagittarius A is the anchor of our galaxy. Everything in the Milky Way, billions upon billions of stars and countless clouds of dust and gas, is bound together by its gravitational influence. It is, in a sense, the beating heart of our cosmic home. Now, nestled uncomfortably close to this monstrous black hole is where we find the G2 cloud. Discovered in the early 2010s, G2 is not floating in some peaceful corner of space, far from danger. Instead, it is located right within the galactic center's danger zone, a region astronomers call the central molecular zone. This environment is packed with extreme phenomena. Stars orbiting at incredible speeds, radiation levels that dwarf anything we could imagine on Earth, and of course, the inescapable gravitational pull of Sagittarius A. To put this in perspective, Sagittarius A sits about 26,000 light-years from Earth. That might sound like an immense distance, but on the galactic scale, it's relatively close. And the G2 cloud's orbit carries it into a region where only the bravest, or most reckless, objects dare to wander. The galactic center is not a friendly neighborhood. It's a place where normal gas clouds are routinely torn apart, shredded into ribbons of plasma, and devoured by the black hole. Stars that venture too close risk being stretched and ripped apart by tidal forces. Yet this is precisely where G2 has chosen to make its home. The positioning of G2 is critical to the story of its survival. Its proximity to Sagittarius A means that it is subject to gravitational forces powerful enough to tear most objects to pieces. But instead of being destroyed, the cloud demonstrated resilience in the face of what should have been certain annihilation. Its location makes it not just a cosmic curiosity, but a frontline witness to the battle between fragile matter and one of the most destructive forces in the universe. Scientists have long been fascinated by the galactic center, not only because it houses Sagittarius A, but also because it offers a unique laboratory to test our understanding of gravity, stellar evolution, and black hole dynamics. It is a region cloaked in dense interstellar dust, making it difficult to observe in visible light. But thanks to infrared and radio telescopes, astronomers can peer through that cosmic smog and track the movements of stars and gas clouds orbiting the central black hole. This is how G2 was first noticed, glowing faintly in infrared, a curious little cloud wandering perilously close to the ultimate destroyer. The setting is almost poetic. On one side, we have Sagittarius A, a symbol of ultimate power and destruction, the very definition of cosmic strength. On the other side, we have G2, seemingly weak, insubstantial, and fragile. One would expect such a cloud to stand no chance in the face of such overwhelming forces. Yet the fact that G2 continues to exist in this hostile environment, orbiting near the very heart of the Milky Way, tells us that this is not a simple story of predator and prey. Instead, it's a complex dance between survival and annihilation, between fragility and strength. Understanding the setting of G2 is essential because it provides the dramatic backdrop for everything that follows. The galactic center is the ultimate testing ground for matter. It's where the laws of physics are stretched to their limits, where Einstein's theories of relativity are put on trial, and where new discoveries often overturn what we thought we knew about the universe. To have a gas cloud, something we usually associate with transience and fragility, become a key player in this environment is nothing short of astonishing. When astronomers watch G2 move across the sky near Sagittarius A, they are not just observing a random patch of gas. They are witnessing a confrontation between the universe's most delicate material and its most destructive force. Every orbit, every flare of light, every unexpected survival tells us something new about the balance of forces at play. And because of its location, the G2 cloud has become a kind of cosmic stage actor, performing in one of the most extreme theaters of the cosmos. This makes G2 not just interesting, but profoundly important. Its survival and behavior are directly tied to the most extreme conditions our galaxy has to offer. Without its dangerous orbit, without its proximity to Sagittarius A, G2 would likely have remained an anonymous gas cloud drifting through the void. But because it dances so close to the black hole, it has become a symbol of resilience, a scientific mystery, and a beacon of curiosity for astronomers around the world. And so, when we set the stage for the story of the G2 cloud, we are really setting the stage for one of the most dramatic cosmic events of the modern scientific era. We are zooming into the center of the Milky Way, to the very core of our galaxy, where one of the greatest forces in the universe resides, and where, against all odds, a mysterious gas cloud continues to survive. Before we can truly grasp why the G2 cloud is so remarkable, we need to take a step back and understand what a gas cloud actually is. In the vast theater of the cosmos, gas clouds, also known as nebulae, are some of the most common yet fascinating structures we encounter. They may not have the dazzling brilliance of stars or the intimidating power of black holes, but they play a central role in the life cycle of the universe. At their core, gas clouds are massive accumulations of dust, gas, and sometimes stars, drifting through the vacuum of space. To us on Earth, they may sound flimsy and insignificant, like a cosmic puff of smoke. But in reality, they are sprawling, colossal structures. Some gas clouds stretch across dozens, hundreds, or even thousands of light-years. To put that into perspective, 1 light-year alone equals nearly 6 trillion miles. So even if a gas cloud appears fragile, the sheer scale of it is almost beyond comprehension. The main ingredients of a gas cloud are hydrogen and helium, the two lightest and most abundant elements in the universe. These are the building blocks of stars, planets, and, ultimately, life itself. Mixed in with these gases are small amounts of heavier elements, carbon, oxygen, nitrogen, and others, that were forged inside ancient stars and scattered across the cosmos through violent events like supernova explosions. Interspersed among the gas are tiny grains of dust, made of silicates, carbon compounds, and frozen molecules. Though individually microscopic, when spread across light years of space, these dust particles can collectively form vast, opaque curtains that block visible light from reaching our telescopes. Now, not all gas clouds are the same. Some are regions of stellar birth, known as stellar nurseries. These are the iconic nebulae you might have seen in images from the Hubble Space Telescope, the Orion Nebula, for example, where new stars are being born out of the collapsing clumps of gas and dust. Others are remnants of death, like the Crab Nebula, which is the shattered remains of a star that exploded in a supernova nearly 1,000 years ago. Still others are quiet, cold, and dark, clouds that are not currently forming stars but may one day collapse under their own gravity to ignite new suns. In astronomy, gas clouds are essential because they are both the cradles of creation and the tombs of destruction. They recycle material from dying stars and provide the raw ingredients for new ones. Without them, galaxies would eventually run out of fuel, and the cosmic cycle of birth and death would grind to a halt. But not all gas clouds are destined for such creative or destructive roles. Some, like G2, are wanderers, drifting objects whose ultimate fate depends on where their orbit takes them. And this is where things get particularly fascinating. Because while gas clouds can be massive in size, they are, in terms of density, incredibly diffuse. If you were to scoop up a cup of air here on Earth, it would contain more particles than an entire cubic meter of a typical interstellar gas cloud. They are ethereal, tenuous, and incredibly fragile compared to the harsh environments of space. This fragility is why G2 survival near Sagittarius A is so shocking. A gas cloud, by definition, should be torn apart by the tidal forces of a black hole. Imagine a cloud drifting near the gravitational pull of an object with millions of times the mass of the Sun. Normally, the closer side of the cloud would feel a stronger pull than the far side, creating a stretching effect. Over time, this effect should shred the cloud into strands, like cosmic taffy, until the gas disperses and falls into the black hole. That's the fate most astronomers expected for G2. To add another layer, many gas clouds glow in spectacular ways. When nearby stars shine ultraviolet radiation onto them, the gas becomes ionized, causing the cloud to emit light. This is why nebulae often appear as brilliant, colorful structures in astronomical photographs. In the case of G2, its glow is particularly strong in the infrared part of the spectrum. This makes it visible to telescopes that can pierce through the thick dust of the galactic center, even when visible light cannot escape. That infrared glow is how astronomers first noticed it moving through the hostile environment near Sagittarius A. But let's not forget, while G2 is a gas cloud, it is no ordinary one. Ordinary gas clouds are dispersed, weak, and utterly vulnerable. Yet here is G2, drifting dangerously close to one of the most destructive forces in the universe, and somehow not only surviving, but continuing its orbit. That makes it extraordinary. To fully appreciate why, we must recognize the paradox gas clouds represent. On the one hand, they are some of the most fragile structures in the universe. On the other hand, they are fundamental to cosmic evolution. They hold within them the seeds of stars and planets, and sometimes, as in G2's case, they hold mysteries that defy our expectations. This is what makes them so important to study. They may appear simple, just clouds of dust and gas, but their role in shaping galaxies, birthing stars, and even resisting black holes makes them some of the most dynamic entities in the universe. So when astronomers identified G2 as a gas cloud, the immediate assumption was that its story would be short-lived. Here was a fragile wisp of matter, wandering too close to the jaws of a galactic predator. By all logic, it should have been doomed. Yet as we will see, that assumption was both natural and profoundly wrong. The story of the G2 cloud truly begins in 2011, when astronomers first detected it using some of the most powerful telescopes available on Earth. Up until that moment, this strange object had lived in total obscurity, just another hidden piece of matter drifting in the dense and chaotic center of the Milky Way. But once the instruments locked onto it, G2 immediately became the subject of intense fascination and heated scientific debate. The discovery happened thanks to a team of astronomers led by Stefan Gillesen at the Max Planck Institute for Extraterrestrial Physics in Germany. They were part of a long-running effort to observe the center of our galaxy in infrared light, a wavelength that can cut through the thick clouds of dust obscuring visible light from that region. Without infrared astronomy, the center of the Milky Way would remain hidden from us, cloaked behind vast curtains of cosmic dust. But with these specialized observations, the heart of our galaxy becomes visible, revealing stars whipping around at dizzying speeds and mysterious gas structures moving under the influence of Sagittarius A. It was during one of these observation campaigns, using the European Southern Observatory's Very Large Telescope, VLT, in Chile, that G2 revealed itself. The telescope's adaptive optics system, which compensates for the distortions caused by Earth's atmosphere, allowed astronomers to see faint details in the galactic center with unprecedented clarity. And there it was, a faint, glowing blob of gas moving along a trajectory that seemed to be pulling it dangerously close to the supermassive black hole. At first, astronomers weren't entirely sure what they were looking at. Was this just another dust cloud floating through space? Was it part of some larger structure? Or was it something entirely new? What caught their attention immediately was the fact that G2 wasn't just sitting still. It was moving, and moving fast. Its trajectory suggested that it was heading straight for a near-collision course with Sagittarius A. This was no ordinary observation. This was a chance to witness something astronomers had only been able to model in simulations, a gas cloud being torn apart and consumed by a black hole in real time. For decades, astrophysicists had studied the feeding habits of black holes indirectly, looking at the aftermath of devoured material or watching faint radiation from accretion disks, the swirling bands of matter falling into black holes. But to actually watch a gas cloud fall into a black hole live? That was unprecedented. The discovery sent shockwaves through the astronomy community. Almost immediately after G2 was announced, papers began flooding in, speculating about what would happen when the cloud reached its closest approach to Sagittarius A. Some predicted spectacular fireworks, bright flares of radiation as the black hole gobbled up the gas, producing bursts of X-rays and infrared light. Others suggested a slower process, with the cloud being stretched and shredded into filaments over time. A few even speculated that G2 might not survive the encounter at all. The excitement wasn't just scientific, it was cultural. The discovery made headlines around the world. For the first time, astronomers had identified an object whose destiny was to face one of the greatest monsters of the cosmos, and they had front-row seats to the show. Telescopes around the globe were scheduled to monitor G2 as it made its approach, while space-based observatories were prepared to catch any flashes of high-energy radiation that might signal the black hole's feeding frenzy. But while many astronomers were thrilled, the discovery also sparked intense debate. For one thing, there was disagreement about what G2 actually was. Some argued it was nothing more than a loose gas cloud, fragile and destined to be ripped apart. Others speculated that it might contain a hidden star at its core, cloaked in a shroud of gas and dust, which could allow it to survive the black hole's grip. Still others floated the idea that it might be the aftermath of a stellar merger, two stars colliding and creating a bloated, gas-rich object that only looked like a cloud. This uncertainty made G2 an irresistible puzzle. The more astronomers looked at it, the more questions arose. Why was it glowing so brightly in infrared? Why did it seem to hold together better than expected, even as it began to stretch under the influence of the black hole? And most importantly, what would happen when it reached its closest point to Sagittarius A? The fact that such a fragile-looking object could drift into the lion's den of a supermassive black hole, and yet resist immediate destruction, was both baffling and thrilling. The scientific community became divided into camps, those who believed it would be destroyed, those who believed it might survive, and those who suspected it wasn't what it appeared to be at all. As the years ticked closer to G2's fateful encounter in 2013 to 2014, the sense of anticipation built like the build-up before a cosmic sporting event. Observatories coordinated their efforts. Models were refined. Predictions became bolder. The stage was set for one of the most closely watched astronomical events of the 21st century. And all of it began with that 2011 discovery, when astronomers first noticed a glowing gas cloud wandering far too close to the most dangerous object in our galaxy. Once the G2 cloud was spotted in 2011 and its trajectory became clear, the astronomical community quickly shifted its focus toward what would happen next. The data indicated that G2 was not just passing through some distant region of the galactic center, it was on a direct path toward a close encounter with Sagittarius A, the Milky Way's supermassive black hole. This immediately led to a wave of predictions, and nearly all of them pointed toward one inevitable outcome: destruction. To understand why scientists were so certain of this fate, we need to look at the dynamics of gravity near a black hole. Sagittarius A is more than 4 million times the mass of our Sun. That kind of gravitational power doesn't just pull objects inward, it tears them apart. The phenomenon responsible is called a tidal force. Imagine stretching a rubber band. The closer side of the band feels a stronger pull than the far side, and this difference in force causes the object to elongate. Near a black hole, this effect is extreme. Objects get pulled into long, thin filaments in a process astronomers call spaghettification. For a fragile cloud of gas like G2, which is already diffuse and tenuous compared to stars or planets, tidal forces should have been catastrophic. Predictions suggested that as the cloud approached the black hole, it would be stretched into a thin stream of plasma. Eventually, much of its material would cross the point of no return, the event horizon, and disappear forever. Whatever remained outside would swirl into the accretion disk, heating up to millions of degrees and radiating energy across the electromagnetic spectrum. The models being drawn up around 2011 and 2012 painted a vivid picture. G2 would light up like a cosmic flare as its material was devoured, creating a feeding event that could last for months or even years. This wasn't just theoretical musing, it was an unprecedented scientific opportunity. For the first time, humanity had a chance to watch a supermassive black hole actively consume matter in real time. The initial predictions were so compelling that many astronomers compared the coming encounter to a once-in-a-lifetime experiment, except that it was one orchestrated by nature itself. Telescopes across the world and in space were prepped and scheduled for around-the-clock monitoring of Sagittarius A X-ray observatories like NASA's Chandra X-ray Observatory, radio arrays like the Very Large Array in New Mexico, and infrared facilities like the Very Large Telescope in Chile all readied themselves to catch the spectacle. Some scientists were particularly excited because Sagittarius A is normally quite quiet compared to other supermassive black holes. In galaxies far away, we often see black holes blazing with activity, devouring surrounding matter and shooting jets of radiation across the cosmos. But our own central black hole has been relatively dormant, producing only faint flickers of light. The approach of G2 was seen as the perfect opportunity to wake it up, to see it roar with the kind of ferocity we know it's capable of. Of course, there were also skeptics. A minority of researchers speculated that G2 might not be a simple gas cloud. If it were, they agreed it would almost certainly be destroyed. But if it hid something denser inside, say, a star, then its chances of survival would be much higher. Yet at the time, this was still considered a fringe idea. The prevailing wisdom held that G2 was doomed. And this doom was expected to unfold spectacularly. Predictions circulated that Sagittarius A would brighten by a factor of 10, 100, or even 1,000 in the X-ray spectrum as it devoured the cloud. News outlets picked up on these forecasts, fueling public fascination with the event. Articles declared that we were about to witness a black hole feast. To the scientific community, this wasn't just hype, it was a moment to test decades of theory against direct observation. Another prediction was that the encounter would produce visible changes in the cloud itself. As G2 was stretched and shredded, its appearance would become elongated and distorted. Computer simulations showed it being drawn into a long, noodle-like stream of gas, spiraling inward toward the black hole. By comparing these simulations with actual telescope images, astronomers hoped to refine their models of how matter behaves under extreme gravitational forces. In short, the initial predictions were a mix of scientific rigor and raw excitement. Nearly everyone agreed that G2 would not emerge from its close pass intact. Whether it was stretched into oblivion, partially consumed, or entirely destroyed, its fate seemed sealed. The only debate was how spectacular the fireworks would be. And so, as 2013 and 2014 drew closer, the years when G2 was expected to reach its closest approach, the astronomical world braced for a cosmic show unlike any other. Scientists thought they were about to watch one of the universe's most powerful forces destroy one of its most fragile objects. It was David versus Goliath, only this time, no one believed David stood a chance. For astronomers, the prospect of watching the G2 cloud's encounter with Sagittarius A was more than just an intriguing prediction. It was a monumental scientific opportunity. Why? Because it meant humanity had the rare chance to watch a black hole eat in real time. Normally, black holes are some of the most mysterious and frustrating objects to study. They are, by definition, invisible. Their immense gravity traps even light, leaving only indirect clues about their presence. We know they exist because of the way they influence their surroundings. Stars whip around them at unimaginable speeds. Gas swirls into their depths, heating up and producing bursts of radiation. Sometimes, powerful jets of matter shoot outward from their poles at nearly the speed of light. But most of these events happen on timescales far too long for humans to observe directly. Galaxies evolve over millions of years. Accretion disks flare and dim unpredictably, often leaving us with incomplete snapshots of black hole behavior. That's why G2 was such a big deal. Here was a fragile object heading directly into the grasp of a supermassive black hole. For the first time in modern astronomy, we had advance notice of the event. This wasn't a case of stumbling upon something after it had already happened. This was an opportunity to set up telescopes, coordinate observations across the globe, and prepare to document every stage of the process. It was like knowing in advance that a rare solar eclipse was coming, except instead of the moon blocking the sun, it was a cloud being devoured by a black hole. The potential payoff was enormous. If G2 was torn apart as predicted, astronomers expected to see Sagittarius A brighten dramatically across multiple wavelengths: infrared, X-rays, and even radio. This sudden activity would act like a flare, illuminating the black hole's surroundings and revealing details that are usually hidden in darkness. By carefully analyzing this light, scientists could learn about the behavior of gas under extreme gravitational forces, the feeding habits of supermassive black holes, and the physics of accretion disks. It was also a chance to test our theories. Black holes are often studied through simulations and mathematical models. While these are incredibly powerful, they still rely on assumptions and approximations. Watching a real event unfold would either confirm those models or expose their weaknesses, forcing us to refine our understanding of one of the most mysterious objects in the universe. The timing couldn't have been better. In the years leading up to G2's approach, advancements in telescope technology had made it possible to study the galactic center with unprecedented precision. Instruments like the Very Large Telescope in Chile, the Keck Observatory in Hawaii, and space-based observatories such as Chandra and the Hubble Space Telescope were ready to capture every photon of light the event produced. Even radio arrays like ALMA, the Atacama Large Millimeter Submillimeter Array, were tuned in, prepared to track changes in the flow of material around Sagittarius A. For the broader scientific community, this was also a unifying event. Astronomers around the world, regardless of their specialties, were drawn into the project. Stellar dynamicists, black hole theorists, computational physicists, and observational astronomers all had something to gain. Conferences buzzed with discussions of G2. Research papers speculated about the aftermath. The level of anticipation was so high that some compared it to waiting for a rocket launch or the landing of a spacecraft on another planet. Beyond the scientific significance, there was also something deeply human about the event. The idea of watching a black hole feed, something so violent, so extreme, and yet so far beyond our reach, captured the imagination of people outside the scientific world. Media outlets eagerly reported on it, often describing it in dramatic terms: the cosmic meal, the galactic showdown, or the black hole feast. For the public, it was a chance to engage with the universe in a way that felt immediate and thrilling. For once, we weren't just reading about black holes in theory, we were about to witness one in action. But make no mistake, the biggest reason this was such a big deal was the rarity of the opportunity. Black holes do not feed on large objects very often. In fact, for our own Sagittarius A, events like this may only happen once every few centuries. To have one occurring in our lifetimes, and with enough warning to prepare, was nothing short of extraordinary. Astronomers couldn't afford to miss it. Every instrument available was trained on the galactic center, ready to record the moment when theory met reality. In a way, The excitement surrounding G2 wasn't just about what we hoped to see, it was about the possibility of seeing something we didn't expect. Science thrives on surprises, and when you combine a fragile gas cloud with a supermassive black hole, the outcome is bound to teach us something new, whether or not it matches our predictions. That is why G2's approach was one of the most highly anticipated astronomical events of the early 21st century. It wasn't just a black hole encounter, it was a front-row seat to cosmic history in the making. As the years ticked by after its discovery in 2011, all eyes turned toward the galactic center, where the G2 cloud was on a collision course with destiny. Astronomers knew that between 2013 and 2014, G2 would reach its closest approach to Sagittarius A, the supermassive black hole at the heart of the Milky Way. This was the moment everyone had been waiting for, the encounter between one of the most fragile structures in space and one of the most destructive forces in the universe. From the earliest observations, G2's orbit was plotted with meticulous precision. Using data from the Very Large Telescope, VLT, in Chile and the Keck Observatory in Hawaii, astronomers tracked the cloud's movement across the dense, dust-choked galactic center. They found that G2 was following a highly elongated, eccentric orbit, like a comet swooping around the Sun, only on a vastly larger and more dangerous scale. The orbit was so stretched that at its farthest point, G2 was relatively safe, drifting tens of thousands of astronomical units, AU, from Sagittarius A. But at its closest point, or periaps, it would pass within a hair's breadth, on the cosmic scale, of the black hole's event horizon. By mid-2013, G2 was already well within the black hole's gravitational influence. Astronomers watched as its shape began to distort. Images showed the once compact cloud starting to elongate, a telltale sign of tidal forces at work. This matched the predictions perfectly. G2 was being stretched into a filament, pulled more strongly on the side closer to Sagittarius A than on the side farther away. To many, it seemed that the clock was ticking down to the inevitable moment of destruction. In early 2014, the anticipation peaked. The closest approach was expected around March or April of that year, though the exact timing was uncertain. Telescopes around the world and in space were pointed at the galactic center almost continuously. Observatories monitored not just the infrared glow of the cloud itself, but also the surrounding X-ray and radio emissions that might signal the black hole's feeding frenzy. What made this approach particularly dramatic was just how close G2 was expected to come. Estimates suggested it would pass within about 200 astronomical units of the black hole, roughly 20 times the distance from the Sun to Pluto. That might sound enormous, but for a supermassive black hole, it's uncomfortably close. At that range, the gravitational pull is so intense that even stars whipping around Sagittarius A at thousands of kilometers per second have their orbits bent like toy marbles caught in a whirlpool. For a fragile gas cloud, the odds of survival seemed vanishingly small. Astronomers expected the approach to play out like this. As G2 neared periaps, it would be stretched further and further until it was torn into shreds. Its gas would begin to spiral inward, colliding with other material and heating up to millions of degrees. This would cause Sagittarius A to flare brightly in X-rays and infrared, perhaps for the first time in living memory. The entire event could take months or years to unfold, offering scientists a treasure trove of data on black hole accretion processes. And so, in the months leading up to periaps, scientific papers poured out. Some researchers modeled how the cloud would fragment. Others calculated how bright the black hole would become as it fed. A few even speculated that the event might kickstart a new era of activity for Sagittarius A, transforming it from its current quiet state into something resembling the blazing quasars seen in distant galaxies. When the moment of closest approach finally came in 2014, the astronomical community held its collective breath. Telescopes scanned the skies. Data poured in. This was the showdown: G2 versus Sagittarius A, fragility versus power. The predictions of tidal shredding and fiery accretion were about to be tested against reality. But what unfolded was not what anyone expected. As the G2 cloud drifted ever closer to Sagittarius A during its 2013 to 2014 approach, expectations of its fate grew more vivid and more dramatic. To most astronomers at the time, the outcome seemed almost guaranteed. G2 was destined for annihilation. A fragile, wispy cloud of hydrogen and dust stood no chance against the gravity of a supermassive black hole. The reasoning behind this confidence was grounded in physics. Black holes exert their power not just by pulling objects inward, but by applying tidal forces, differences in gravitational pull across an object. For something dense and compact, like a star or planet, these tidal forces can be resisted, at least until the object ventures too close. But for something diffuse, like a gas cloud, it's a different story. The side of the cloud closer to Sagittarius A would feel a much stronger gravitational pull than the far side. The result would be catastrophic stretching, elongating the cloud like a piece of cosmic taffy until it fragmented into smaller streams of gas. Astronomers ran computer simulations of this scenario, and the results were spectacular. In these models, G2 didn't just stretch, it unraveled. Its gas was drawn into thin filaments, swirling around the black hole like ribbons in a whirlpool. As the gas fell inward, it collided with other material near the black hole, heating up to millions of degrees. This process, known as accretion, was expected to unleash a burst of energy. For an otherwise quiet black hole like Sagittarius A, this would have been a dramatic awakening. The predictions varied in their specifics, but the general theme was the same: destruction on a cosmic scale. Some models suggested that G2 would be completely devoured, with every atom of its gas swallowed into the black hole. Others proposed a slower demise, where pieces of the cloud would survive temporarily but eventually spiral inward over years or decades. Either way, the consensus was clear: G2 would not survive intact. The destruction was expected to be spectacularly visible. As the gas heated, astronomers predicted Sagittarius A would brighten across multiple wavelengths. X-rays would flare as the hottest gas radiated energy. Infrared telescopes would detect glowing filaments of dust and gas. Even radio waves might spike as the black hole's environment was disturbed. The galactic center, normally quiet and faint compared to active galaxies elsewhere in the universe, was predicted to put on a rare show of fireworks. This expectation of destruction wasn't just about curiosity, it was about science. If Sagittarius A lit up as expected, it would provide a once-in-a-lifetime opportunity to study black hole feeding behavior in detail. For decades, astronomers had studied active black holes in distant galaxies, but those events were happening millions or billions of light-years away. With G2, the feeding event would occur in our cosmic backyard, just 26,000 light-years from Earth. It was like having a laboratory experiment staged by nature itself, offering an unprecedented chance to test theories of accretion, radiation, and tidal disruption. Because of this, the astronomy community prepared extensively. Observatories around the world coordinated campaigns to monitor Sagittarius A continuously during G2's approach. Infrared, X-ray, and radio telescopes were all aligned, ready to capture every detail of the anticipated destruction. Some researchers even speculated that the black hole's feeding frenzy might continue for years, providing an ongoing stream of data. To the public, the predictions sounded like the stuff of science fiction. News outlets described it as a cosmic meal or feast, with the black hole about to devour a hapless cloud. Headlines promised dramatic flares of energy and a rare chance to watch a black hole in action. For once, the public's imagination and the scientific community's expectations were perfectly aligned. Everyone was waiting for the fireworks. The imagery used in scientific talks and papers reflected this sense of drama. Simulations showed G2 being ripped apart, its gas streaming toward the black hole in brilliant, glowing arcs. Illustrations depicted the black hole lighting up as it consumed the cloud. The narrative was compelling and seemed inevitable. A fragile cloud meets a cosmic predator, and only one can emerge. But here's the key point: those expectations were built on the assumption that G2 was exactly what it appeared to be, a simple gas cloud. If that assumption was wrong, the predictions of destruction would be wrong too. Still, at the time, very few entertained the possibility that anything else could happen. To most astronomers, the idea of survival seemed absurd. And so, as G2 reached its closest approach in 2014, the world braced for the cosmic spectacle of its destruction. Scientists, students, and space enthusiasts all turned their attention to Sagittarius A, waiting to see the black hole light up as it feasted on its victim. But what happened next would defy every expectation. As 2014 unfolded and the G2 cloud made its perilous swing around Sagittarius A, the astronomical community held its collective breath. For years, the narrative had been clear: this fragile gas cloud was going to be shredded, stretched, and consumed by the gravitational monster at the center of the Milky Way. Telescopes were locked on target. Observatories across the world and in orbit stood ready to record the anticipated fireworks. Scientists expected a galactic drama, a feeding frenzy that would transform Sagittarius A from its usual quiet state into a roaring, luminous engine. But then, nothing happened. Or rather, something did happen, but not what anyone predicted. Instead of being annihilated, G2 emerged from its closest approach battered but unmistakably intact. It wasn't torn into ribbons. It wasn't swallowed whole. The massive flares of X-rays and radio waves astronomers expected to see never materialized. Sagittarius A barely flickered. It was as though the black hole had ignored its would-be meal altogether. This outcome stunned the scientific community. Here was a diffuse, fragile cloud of gas, something that should have been shredded instantly under the tidal forces of a supermassive black hole, and yet, it survived. The simulations, the predictions, the headlines about a cosmic feast, all of it was suddenly thrown into question. When astronomers compared images of G2 before and after periapse, they saw something remarkable. The cloud was still glowing in infrared. It had been stretched a little, yes, and perhaps lost some material, but it was still very much there. Not a filamentary smear, not a faint trace of former existence, but a recognizable, coherent object. G2 had gone toe-to-toe with one of the most destructive forces in the universe and walked away. This was more than just unexpected. It was paradigm-shifting. If G2 had been a simple gas cloud, as most scientists assumed, it should not have survived. The survival implied that G2 wasn't what it first appeared to be, or that our understanding of the environment near Sagittarius A needed serious revision. Suddenly, what had been framed as a predictable event became one of the great astronomical mysteries of the decade. For many scientists, this survival was deeply frustrating and deeply exciting all at once. On the one hand, years of build-up and preparation had not produced the spectacular show they had promised the world. Sagittarius A hadn't flared dramatically. The predicted feeding frenzy never happened. From that perspective, it seemed anticlimactic. On the other hand, G2's survival was, in its own quiet way, far more fascinating than its destruction would have been. A black hole shredding a gas cloud would have been spectacular but expected. A gas cloud surviving the encounter was genuinely shocking, and that shock opened up a universe of new questions. Why didn't Sagittarius A react more violently? Why didn't the tidal forces tear G2 apart? What allowed this seemingly fragile object to endure? Was it possible that G2 wasn't a cloud at all, but something denser disguised in a cloud's clothing? Astronomers began re-examining the data, poring over every detail of the infrared images, the faint X-ray measurements, and the subtle changes in G2's trajectory. What they found was that while G2 had been distorted somewhat by the encounter, its core remained surprisingly compact. This hinted that there might be something solid, or at least denser, hidden inside. The survival of G2 also reframed the entire event in terms of cosmic strength. We typically think of strength as raw power, but here was an example of strength as resilience. A fragile-looking object had endured one of the most extreme environments in the galaxy, resisting forces that should have obliterated it. That resilience was, in its own way, a form of cosmic might. In the years since, G2 survival has continued to baffle and intrigue astronomers. It sparked new theories about what G2 really is, and those theories range from the idea of a star cloaked in gas, to the aftermath of a binary star merger, to something entirely unprecedented. Each theory attempts to answer the same question: how could G2 have survived? And so, instead of being remembered as the gas cloud that was destroyed by a black hole, G2 has gone down in history as the gas cloud that refused to die. Its unexpected resilience turned it from a victim into a mystery, and mysteries, as every scientist knows, are often far more valuable than predictions fulfilled. The survival of the G2 cloud after its close brush with Sagittarius A was not just unexpected, it was downright shocking. To understand why astronomers were left scratching their heads, we need to revisit the fundamental idea of what happens when a fragile object, like a cloud of gas, encounters a supermassive black hole's tidal forces. A black hole's gravity isn't just strong, it's uneven. Objects closer to the black hole are pulled with more force than those farther away. For solid, compact objects, like stars or planets, This effect can be resisted up to a point because the object's self-gravity and internal structure hold it together. But for something diffuse, like a gas cloud, there's no such cohesion. The molecules are only loosely bound, drifting like smoke in a cosmic breeze. When tidal forces act on such a cloud, they should easily tear it apart, stretching it into thin filaments before scattering it into oblivion. This was the expectation for G2. Astronomers believed that as it reached periaps, the closest point in its orbit, around Sagittarius A, the cloud would unravel, leaving little more than a faint smear of gas glowing in infrared. The black hole would then consume part of that gas, producing flares of X-rays and infrared light that would confirm decades of theoretical models about how black holes eat. But instead, G2 survived. It didn't behave like a delicate puff of cosmic smoke. It remained coherent. This is the crux of the mystery. For a gas cloud, survival in that environment should have been impossible. The physics, as understood at the time, gave it no chance. Yet there it was, still orbiting, still glowing, still undeniably intact. The shock came from the sheer scale of the forces involved. Sagittarius A is over 4 million times the mass of the Sun. Its tidal forces are so immense that stars orbit it at thousands of kilometers per second, completing loops in mere years rather than millennia. To give you a sense of scale, if Earth were placed in G2's position, it wouldn't just be tugged or stretched, it would be pulverized, its atoms scattered across space. Against that backdrop, the idea of a fragile gas cloud holding together seemed absurd. And yet, G2 defied that logic. It wasn't shredded. It wasn't scattered. It wasn't consumed. It endured, and in doing so, it broke the rules, or at least the rules as we understood them. That's what made its survival so mysterious. Astronomers were left with a paradox. Either G2 wasn't a simple gas cloud, or our understanding of black hole tidal interactions was missing something fundamental. The survival of G2 raised more questions than answers. If it wasn't torn apart, what was holding it together? Was there some hidden structure, like a star, acting as an anchor at its center? Was the gas somehow denser or more bound than originally thought? Or was there something about Sagittarius A's environment that softened the blow, sparing G2 when physics suggested it should have been destroyed? Adding to the mystery was the behavior of Sagittarius A itself. If G2 had been shredded and consumed, astronomers expected the black hole to flare dramatically. Instead, it barely reacted. This lack of fireworks suggested that little to no material from G2 had actually been devoured, which only deepened the puzzle. If the gas cloud survived, why didn't it lose enough material to trigger the feeding frenzy everyone anticipated? This is why G2's survival wasn't just surprising, it was revolutionary. It forced astronomers to reconsider their assumptions, to entertain possibilities that had seemed unlikely or even absurd just a few years earlier. Was G2 actually a star cloaked in gas? Was it the remnant of a stellar collision? Was it a hybrid object, something entirely new to science? In the end, the mystery of G2 wasn't just about what it was. It was about what its survival said about the universe itself. It revealed that even in the most extreme environments, there are still surprises waiting to overturn our understanding. It showed that fragility and resilience are not always what they seem. And it reminded us that when we think we know how the cosmos works, the universe often has a way of humbling us. When the G2 cloud emerged from its perilous encounter with Sagittarius as seemingly unscathed, the astronomical community was left with a burning question. How could something so fragile survive one of the most destructive environments in the galaxy? The only logical conclusion was that G2 wasn't what it first appeared to be. If it wasn't a simple, shapeless puff of gas, then what was it? This is where the theories began to multiply. Almost immediately after G2's survival became clear, scientists proposed that the cloud might not be entirely diffuse. Instead, it could be hiding a dense core inside, a gravitational anchor that kept the cloud together even as the black hole's tidal forces tried to rip it apart. The idea of a dense core inside G2 made sense. Gas alone, drifting through space, should have been shredded and scattered. But if the gas were merely a surrounding envelope, cloaking something sturdier, then survival was not only possible but even probable. That hidden object could provide the gravitational pull necessary to hold the surrounding gas in place, preventing the cloud from unraveling. So, what could this hidden core be? The most obvious candidate was a star. Stars are dense, compact, and capable of withstanding tidal forces that would annihilate a gas cloud. If G2 were actually a star wrapped in a thick shroud of dust and gas, it would explain both its glowing infrared appearance and its resilience during the encounter with Sagittarius A. Astronomers pointed to the way G2 glowed in infrared as evidence supporting this theory. A simple gas cloud should have dissipated more dramatically, but a star inside the cloud could provide a constant source of illumination, keeping the cloud visible even as it passed through the black hole's gravitational field. In this model, what telescopes were seeing wasn't just gas, but gas illuminated and sustained by the heat of a star buried within. Others took this core theory in different directions. Perhaps G2 wasn't just one star but the result of a more dramatic event, a stellar collision. If two stars had merged in the dense, chaotic environment near Sagittarius A, the result could be a bloated object surrounded by a thick shell of gas and dust. Such a merger would naturally produce a strange, oversized envelope, making the object appear at first glance to be a simple cloud. This binary star merger theory became one of the most compelling explanations for G2 survival, but we'll go deeper into that shortly. Yet another possibility was that G2 wasn't entirely unique, but part of a larger class of mysterious objects near Sagittarius A. Observations in later years suggested there were several other compact, cloud-like bodies orbiting close to the black hole. Could G2 be one of many such hybrid objects, each with dense cores wrapped in dusty envelopes? If so, its survival wasn't a fluke, it was a feature of a whole new category of astrophysical phenomena. The core theory also helped explain why Sagittarius A didn't flare up as much as expected. If G2 were just a cloud, large amounts of gas should have been stripped away and devoured by the black hole, producing massive bursts of energy. But if most of G2's material was gravitationally bound to a central object, only a small fraction of the gas would have been stripped. That meant less fuel for Sagittarius A, and therefore fewer fireworks for astronomers to observe. This line of reasoning marked a major shift in how scientists approached G2. No longer was it viewed as a doomed cloud of gas on a suicide mission. Instead, it became a puzzle piece in a larger cosmic picture, a clue that the region near Sagittarius A might be full of unusual, resilient objects masquerading as fragile clouds. Of course, the dense core theory is still a theory. No telescope has yet directly revealed the inner workings of G2, but it provides a framework, a way to reconcile the paradox of a fragile-looking cloud surviving an encounter with a supermassive black hole. Whether the core is a star, a merged remnant, or something stranger, it has transformed G2 from a simple curiosity into one of the most tantalizing mysteries in modern astronomy. One of the most compelling explanations for G2's surprising resilience is the star at the core theory. This idea proposes that G2 is not merely a drifting clump of interstellar gas and dust, but instead a star cloaked in a dense, extended envelope of material. This seemingly simple reinterpretation completely reshapes the way astronomers understand G2's behavior, and it provides a logical explanation for how the cloud survived its perilous journey around Sagittarius A. To grasp the power of this theory, consider the difference between a gas cloud and a star. A gas cloud is diffuse, its atoms and molecules are spread out, loosely held together by nothing more than their collective motion. A star, on the other hand, is compact and gravitationally bound. Its immense self-gravity pulls matter tightly toward its center, giving it the internal cohesion to resist external tidal forces. If G2 were just a puff of gas, it should have been shredded and consumed without resistance. But if there's a star hidden at its heart, then everything changes. Imagine a star embedded in a thick, dusty shroud. From a distance, what you see is the glowing envelope of gas, illuminated by the star inside. To infrared telescopes, this would look very much like a cloud. In fact, the gas and dust around the star could easily obscure its stellar light, masking the fact that a compact core lurked beneath the haze. This would explain why G2 was initially interpreted as a cloud and why it continued to shine in infrared light even after its close encounter with the black hole. The star's heat could replenish and sustain the envelope, preventing it from dispersing entirely. The star at the core model also accounts for G2's resilience during its closest approach to Sagittarius A. As tidal forces stretched the surrounding gas, the star's gravity acted like an anchor, pulling much of the material back into orbit around itself. Yes, some gas may have been stripped away, but not enough to completely unravel the object. The result was survival, not as a loose cloud, but as a cloaked star stubbornly holding onto its outer layers. There are other intriguing details that support this theory. For example, astronomers noticed that G2's brightness in infrared remained relatively steady before and after periapse. If G2 were just gas, it should have dimmed significantly as material was stripped away. But if the glow was sustained by a central star heating the gas and dust, then it makes sense that the brightness would persist. It's like having a lamp hidden inside a fog bank. As long as the lamp is burning, the fog will glow. The environment near Sagittarius A also makes the existence of such shrouded stars plausible. The galactic center is dense and chaotic, filled with stars, stellar remnants, and swirling gas. Interactions between stars can create exotic objects, including stars with bloated envelopes or stars shrouded in dust from collisions or mergers. If G2 is one such object, it may be just one of many cloaked stars orbiting dangerously close to the black hole. There's another fascinating implication of this model. If G2 is a star wrapped in gas, then the black hole encounter may have stripped away some of that envelope, gradually revealing the stellar core within. In other words, G2 may change its appearance over time. Future observations could show it shrinking, becoming more compact, or shining differently as it sheds its outer layers. Watching G2 evolve in this way could provide scientists with rare insights into how stars survive and adapt in extreme environments. Critics of the star-at-the-core theory argue that while it neatly explains G2's survival, it requires assumptions that have yet to be proven. We don't yet have direct evidence of the hidden star, only indirect clues. Still, the theory remains one of the most widely accepted explanations for G2's resilience, and it has reshaped the conversation around this mysterious object. If true, the star-at-the-core theory transforms G2 from a fragile, doomed gas cloud into something far more interesting. A disguised star, cloaked in a dusty veil, defying destruction in one of the harshest neighborhoods in the cosmos. It turns what looked like weakness into a hidden strength, revealing that appearances in the universe can be profoundly deceptive. Another powerful explanation that has captured the imagination of astronomers is the binary star merger theory. This idea suggests that G2 may not simply be a lone star wrapped in gas, but instead the bizarre aftermath of a cosmic collision, the merger of two stars. The galactic center, where G2 orbits, is not a calm, orderly place. It is a dense and violent environment, filled with stars packed more tightly together than in almost any other region of the galaxy. These stars move at blistering speeds, driven by the gravitational grip of Sagittarius A. In such a crowded and chaotic arena, close encounters are inevitable. Stars can gravitationally interact, slingshot around one another, and sometimes, in rare but spectacular cases, collide and merge. When two stars merge, the event is dramatic. Their outer layers blend together in a violent dance of heat, light, and turbulence. The result is not a clean, compact star like the ones we see in the night sky, but a swollen, unstable object. It becomes bloated, shrouded in gas and dust, and surrounded by the debris of the merger. Such an object would look, from a distance, almost exactly like a gas cloud. This is where G2 enters the picture. According to the binary star merger theory, G2 could be the lingering remnant of such a stellar collision. The newly formed star, hidden deep inside, would act as the gravitational anchor, while the bloated, extended envelope of gas and dust would give it the appearance of a diffuse cloud. This would perfectly explain why G2 survived its close pass with Sagittarius A. The dense stellar core held everything together, even as the surrounding material was tugged and stretched by tidal forces. The idea becomes even more compelling when you consider the timelines. Stellar merger remnants don't remain bloated and enshrouded forever. Over thousands to millions of years, the extended envelope of gas gradually dissipates, leaving behind a more normal-looking star. If G2 is indeed a merger remnant, then astronomers may have caught it during a fleeting phase of its evolution, right in the middle of its recovery from a cosmic collision. That would make it not only resilient, but also extraordinarily rare and valuable as an object of study. The merger theory also helps explain another mystery: why G2 appears so unusual compared to typical gas clouds. Normal clouds of dust and hydrogen in the galaxy lack any real cohesion and would have been shredded long before reaching periapse. But if G2 is the product of a stellar merger, its strange hybrid nature, part star, part shroud, would naturally account for its resilience. It is not a pure gas cloud but a complex system with an inner engine of gravity and heat. Some astronomers have pointed to the fact that G2 doesn't appear to be completely unique. In recent years, several other G-type objects have been spotted orbiting close to Sagittarius A. These mysterious, cloud-like bodies all share similar properties: diffuse envelopes, infrared emission, and surprising coherence in the face of black hole tidal forces. This raises the possibility that G2 isn't alone, but part of a whole population of merger remnants near the galactic center. If so, stellar mergers might be far more common in this dense region than previously thought. The binary star merger theory paints G2 as something extraordinary, a cosmic survivor forged not in calm, steady stellar evolution, but in the chaos of collision. Instead of being destroyed by the black hole, it may have been born from destruction itself. Its survival during periapse would then be a story not of fragility, but of resilience rooted in its violent origin. Of course, as with all theories, there are uncertainties. Astronomers cannot yet confirm directly that G2 is a merger remnant. But the theory is attractive because it explains not only G2's endurance, but also its strange glowing envelope and its resemblance to other mysterious objects near Sagittarius A. It ties together multiple puzzles into a single, elegant narrative. G2 is what happens when stars collide in the heart of the galaxy. If this theory is correct, then G2 is more than just a survivor. It is a symbol of cosmic transformation. It represents how destruction in the universe often leads to creation, how chaos can give birth to resilience, and how even in the shadow of a black hole, life cycles of stars continue in unexpected and awe-inspiring ways. The survival of the G2 cloud against the immense gravitational might of Sagittarius A has been described by many astronomers as nothing short of miraculous. To put it into perspective, we are talking about an object that drifted into the gravitational well of a supermassive black hole, an entity capable of crushing entire stars, warping space and time, and bending light itself. Yet, against all expectations, G2 resisted. It endured. In doing so, it has come to be seen as a kind of supermassive shield, an object whose resilience has redefined what we consider strength in the cosmos. To understand why this is so extraordinary, consider the scale of forces at play. Sagittarius A is about 4 million times the mass of our Sun. At the distances G2 approached, just a few hundred astronomical units from the black hole, the tidal forces are powerful enough to rip apart almost anything not bound by extraordinary cohesion. Even stars that wander too close can be torn into streams of matter, producing dazzling displays known as tidal disruption events. A fragile cloud of gas and dust should have stood no chance. And yet, G2 didn't disintegrate. Instead, it behaved more like a fortress than a fog bank. It may have been stretched slightly, and perhaps it lost some of its envelope, but the object as a whole remained intact. To survive such an encounter is not just resilience, it is a testament to a hidden strength that defied every model and prediction. Astronomers often describe black holes as the ultimate destroyers. They represent cosmic inevitability. Once you cross their event horizon, no amount of strength or resistance can save you. But G2 never crossed that fatal boundary. Instead, it came close enough to be within the black hole's deadly influence zone, a region where tidal forces usually dictate annihilation. By emerging from this zone intact, G2 showed that not everything near a black hole is destined for destruction. In fact, some objects can resist and endure, even thrive, under such extreme conditions. This resistance reframes how we think about strength in the universe. Typically, we assign strength to things that are massive, compact, or violent, like neutron stars, quasars, or the black holes themselves. But G2's survival reveals another kind of strength, the ability to endure forces that should be impossible to endure. It's not about brute force, it's about resilience. G2's strength is subtle, hidden beneath its fragile-looking cloak of gas and dust. Yet it is precisely this hidden strength that allowed it to act like a shield against the destructive pull of Sagittarius A. Even more astonishing is the symbolism of this survival. In a universe dominated by entropy and destruction, where even the mightiest stars eventually collapse and die, G2 represents resistance. It represents the possibility that the universe is filled with hidden layers of resilience that we have yet to understand. This is why some scientists and storytellers alike refer to G2 as one of the most resilient objects ever observed near a black hole. The supermassive shield metaphor also resonates because of what it implies for the galactic center. If G2 is not alone, if other such objects exist cloaked in gas and dust, then the region near Sagittarius A is not just a graveyard where stars are destroyed, but a crucible where new and unusual forms of resilience emerge. G2 might be the first of many such objects we've caught in action, showing that survival is not just possible, but perhaps common, even in the harshest of cosmic environments. Of course, its survival does not mean it was unaffected. The envelope of gas surrounding G2 likely interacted with Sagittarius A's environment, possibly shedding some material or altering its shape. But the fact that a recognizable, coherent object emerged afterward is the key. Where predictions foresaw obliteration, reality delivered endurance. G2 stood against the unimaginable gravity of a supermassive black hole and held together, a cosmic David against a gravitational Goliath. This resilience has elevated G2 from being just another curiosity to something legendary in the field of astronomy. It is no longer merely a cloud orbiting the galactic center. It has become a symbol of cosmic strength, of resistance against overwhelming odds. For astronomers, it is a reminder that the universe is never short on surprises. For the public, it is a story of survival in the face of certain destruction. Why call the G2 cloud the strongest object in the universe? At first glance, it seems counterintuitive. When we think of strength in the cosmos, our minds usually leap to neutron stars with their crushing densities, black holes with their unstoppable gravity, or even titanic galaxies that span hundreds of thousands of light-years. Compared to these giants, G2 looks frail, just a hazy cloud of dust and gas drifting through space. But strength is not always about size, mass, or violence. Sometimes, true strength reveals itself in survival. G2 was expected to die. All the equations, all the models, all the simulations pointed toward its destruction. A diffuse gas cloud should have been no match for the tidal forces of Sagittarius A, the supermassive black hole lurking at the center of our galaxy. It was supposed to unravel, to stretch into a ribbon, to scatter into streams of matter that would feed the black hole's hunger. In fact, astronomers were almost giddy at the thought of witnessing such a spectacular death in real time. Yet G2 didn't die. It lived. And in doing so, it displayed a kind of strength that defied every expectation. Consider the context. Sagittarius A is one of the most extreme environments imaginable. It is a gravitational monster, 4 million times the mass of the Sun, whose influence warps the orbits of nearby stars into dizzying ellipses. At its event horizon, escape becomes impossible. Not even light can flee. To survive and approach this close is to endure one of the greatest destructive forces in the universe. And that's exactly what G2 did. This is why astronomers began to speak of G2 in terms of resilience. The black hole had every advantage: gravity, tidal force, inevitability. G2 had none. It appeared fragile, diffuse, and weak. But in the end, appearances were deceiving. Whether because it harbored a star at its core, or because it was the strange remnant of a stellar merger, or because of some other property we have yet to uncover, G2 resisted. It endured. And in that endurance lies its strength. Strength, in the cosmic sense, can take many forms. Neutron stars are strong because of their density. Quasars are strong because of their brilliance. Black holes are strong because of their unstoppable pull. But G2 showed another kind of strength, the strength of resilience against destruction. It is not the strongest object in the sense of crushing force or mass. It is the strongest because it defied the universal rule that fragility near a black hole means annihilation. It rewrote what survival looks like in one of the deadliest regions of space. To frame it another way, think of strength as the ability to resist forces that should be overwhelming. On Earth, we admire structures that withstand earthquakes or storms. In human life, we admire people who endure hardships that should break them. By the same measure, G2 is strong because it resisted the storm of Sagittarius A. It is strong because it survived the unthinkable. This framing also carries symbolic weight. G2 is not massive like a galaxy, nor compact like a neutron star, but it has shown that even what looks fragile can harbor incredible resilience. It reminds us that strength is not always obvious, and that survival itself is often the greatest measure of power. And perhaps this is why G2 has captured such fascination, not just among scientists but also among storytellers and space enthusiasts. By surviving, It transformed from a doomed object into a legend. It became a cosmic survivor, a beacon of endurance, a reminder that even in the face of overwhelming odds, survival is possible. That is why G2, strange and mysterious though it may be, has earned the title of one of the strongest objects in the universe. Gravity is the architect of the universe. It builds galaxies, binds stars, sculpts planets, and dictates the motions of cosmic bodies on every scale. But gravity is also the destroyer. When it acts unevenly across an object, pulling harder on one side than the other, it creates what we call tidal forces. And these forces can be devastating. To understand tidal forces, let's start small and close to home. On Earth, we experience tides in the oceans because the moon pulls more strongly on the side of Earth that faces it than on the far side. The difference is slight, but it's enough to cause the oceans to bulge, creating high and low tides. Now, scale this concept up to astronomical proportions. Near a black hole, the difference in gravitational pull across even a small object is enormous. These tidal forces can stretch and ultimately tear apart anything that comes too close. Astronomers call this process spaghettification, a dramatic term for the very real fate awaiting stars, planets, or unlucky gas clouds caught in the grip of a black hole. This is exactly what scientists expected would happen to G2. As it approached Sagittarius A, the side of the cloud nearest the black hole should have been pulled far more strongly than the far side. A gas cloud has no rigid structure and very little gravity of its own to fight back. In theory, it should have unraveled like a wisp of smoke blown into a storm. The cloud should have stretched into long, thin filaments, scattering its material into the black hole's environment. Portions of it should have spiraled inward, feeding Sagittarius A and lighting up the galactic center with bursts of radiation. But that's not what happened. G2 defied the rule. Instead of being torn apart by tidal forces, it held together. Yes, it was distorted somewhat. It elongated slightly during its closest approach, but when it emerged on the other side of its orbit, it was still coherent, still glowing, still unmistakably intact. This baffled astronomers because it suggested that G2 was not the fragile object they thought it was. Why did G2 resist tidal destruction when physics said it shouldn't have? The most compelling explanation is that it wasn't just a simple cloud. If G2 contained a dense, compact core, like a star or the remnant of a stellar merger, that core would have acted like an anchor. The gas surrounding it might have stretched, but the central object's gravity would have pulled much of the envelope back, preventing complete disintegration. Essentially, the hidden core could shield G2 from the worst effects of tidal forces, allowing it to survive what should have been a death sentence. Another possibility is that G2's gas was denser and more gravitationally bound than astronomers originally assumed. If its internal gravity was stronger, it could resist being pulled apart, at least enough to maintain its integrity. This idea fits with later observations suggesting that G2 wasn't alone. Other compact, cloud-like bodies orbit Sagittarius A as well, hinting at a population of resilient objects masquerading as fragile gas clouds. The key point is this: gravity was supposed to be the executioner. Tidal forces should have shredded G2 into nothingness. Instead, G2 revealed a hidden resilience that flipped the script. It showed that even in the domain of the universe's most destructive forces, survival is possible if an object has the right inner strength. In this sense, G2 is not just a survivor, it's a rebel against the natural order as we understand it. By defying the rule of tidal forces, it challenged our models of how black holes interact with their surroundings. It reminded scientists that gravity, for all its predictability, still has the capacity to surprise us when unusual or hidden structures are at play. When word spread that G2 was heading on a collision course with Sagittarius A, the astronomical community was electrified. From the moment of its discovery in 2011, researchers had anticipated that its periapse, its closest approach, would occur sometime between 2013 and 2014. Yet the actual unfolding of events transformed anticipation into a global scientific spectacle. Observatories around the world, equipped with cutting-edge infrared, X-ray, and radio instruments, became focal points of an unprecedented monitoring effort. The excitement was palpable, as astronomers prepared to witness, live, a cosmic event that had been theorized but never directly observed before: a black hole interacting in real time with an object on the edge of destruction. Unlike many astronomical phenomena, which are either too distant, too slow, or too infrequent to observe in detail, the approach of G2 offered a tangible, almost cinematic, window into high-energy astrophysics. Coordinated observation campaigns were launched, spanning continents and orbital platforms. Telescopes in Chile, Hawaii, and the Canary Islands trained their sights on the galactic center, while space telescopes such as Hubble and Chandra were redirected to capture infrared and X-ray signatures. The monitoring wasn't casual. It was a worldwide marathon of observation, analysis, and theoretical anticipation. The sense of excitement among astronomers stemmed from multiple factors. First, there was the uniqueness of the event itself. Black holes, particularly supermassive ones like Sagittarius A, are usually studied indirectly. Scientists infer their presence and behavior through the motion of surrounding stars, the distribution of gas, and the radiation emitted from accretion disks. Directly observing a black hole interacting with a passing object, especially one with advance notice, was nearly unprecedented. It was as if the universe had provided a real-time laboratory experiment for something previously relegated to simulations and theory. Second, there was the level of detail that could be obtained. As G2 approached, its motion, brightness, and structure could be tracked week by week, month by month. Infrared observations allowed astronomers to see through the dense dust in the galactic plane, revealing subtle changes in the cloud's shape. X-ray observatories were primed to detect any sudden outbursts from the black hole if G2's material was being accreted. Radio telescopes monitored interactions between G2's gas and the surrounding galactic center medium. The event's multi-wavelength coverage made it a rare opportunity to collect comprehensive data on both the cloud and the black hole simultaneously. Social and academic networks buzzed with activity. Conferences, webinars, and collaborative online platforms were flooded with live updates. Scientists compared simulations with incoming data, adjusting models in real time. The tension was almost cinematic. What would happen when G2 reached its closest point? Would the black hole flare spectacularly? Would the cloud be torn into ribbons of gas? Could a new phenomenon emerge that nobody had anticipated? The anticipation was not limited to professional astronomers. Media outlets picked up the story, translating complex astrophysics into a narrative that captured public imagination. Descriptions ranged from a cosmic feast to a black hole showdown. Space enthusiasts and students worldwide followed live feeds from observatories and read real-time updates from astronomers on social media. This wasn't just an academic exercise. It became a shared global experience, uniting professionals and amateurs alike in their fascination with the extremes of the universe. When G2 finally reached its periaps in 2014, the tension was electric. Observatories captured high-resolution images and spectral data that were immediately circulated and analyzed. While the dramatic shredding predicted by simulations did not occur, the collective focus on G2 and Sagittarius A during those months created an astronomical shockwave, a surge of interest, debate, and discovery that rippled across the scientific community. Papers were drafted in near real time, theoretical models were revised, and countless presentations were made highlighting the unusual behavior of the cloud. Perhaps most importantly, the global excitement underscored a deeper truth about science itself. It thrives on uncertainty and surprise. The unexpected survival of G2, while anticlimactic to some in terms of explosive phenomena, generated even greater intrigue. Astronomers were compelled to reconsider their understanding of tidal forces, cloud dynamics, and stellar evolution near supermassive black holes. The collaborative intensity, the live observation campaigns, and the rapid dissemination of data created a scientific event that was as much about human curiosity and coordination as it was about the object itself. In short, G2's approach did not just illuminate the galactic center. It illuminated the global astronomical community, creating a ripple of excitement and intellectual engagement that spanned continents. It was a rare opportunity to witness the universe in action, live, and to grapple with a phenomenon that challenged long-standing assumptions. Even after the dust settled, the impact of this observational campaign continued to influence research priorities, telescope scheduling, and theoretical work in the years that followed. As the months of anticipation reached their climax during G2's closest approach to Sagittarius A in 2014, astronomers braced themselves for what many predicted would be a spectacular cosmic fireworks show. Simulations and theoretical models suggested that as the cloud came under the immense tidal forces of the black hole, it would be shredded into streams of gas, which would then spiral inward, collide, and heat up, producing dazzling bursts of X-rays, infrared light, and radio emissions. The expectation was that Sagittarius A, usually a relatively quiet supermassive black hole, would erupt with visible activity, feeding voraciously on G2's material and perhaps lighting up the galactic center like a miniature quasar. For months, telescopes around the world and in space were trained on the galactic core, poised to catch every flicker, flare, and shockwave. Astronomers, both professional and amateur, were primed for drama. Media outlets prepared headlines describing a black hole feasting in real time. The world was ready for an extraordinary spectacle. And then G2 passed periaps. The reality was anticlimactic. Observations showed little more than modest changes in the cloud structure. There were no massive X-ray outbursts, no brilliant flares, no dramatic feeding frenzy for Sagittarius A. The black hole remained quiet, almost indifferent, as G2 skirted by. The high-energy fireworks that simulations predicted never materialized. For some, this was a letdown. The moment had been hyped as a rare, cosmic display of destruction, and in that sense, it didn't deliver. Yet the anticlimax itself was fascinating. The lack of dramatic flares indicated that very little of G2's mass was actually accreted by the black hole. This observation forced astronomers to reconsider the nature of G2. If it had been a simple gas cloud, the expectation was that significant portions would have been stripped and consumed. Its survival, combined with the subdued response of Sagittarius A, suggested that G2 was more cohesive than initially believed, likely containing a dense core, possibly a star or a merger remnant, holding the surrounding gas in place. The anticlimactic nature of the event also revealed something important about black hole physics. Models of accretion and tidal disruption rely on assumptions about the density, composition, and structure of objects falling toward black holes. G2 demonstrated that these assumptions might not always apply, especially in cases where an object masquerades as fragile but is internally dense. The absence of a feeding frenzy highlighted the need for more nuanced models, emphasizing the interaction between central cores, surrounding envelopes, and tidal forces. For the astronomical community, the anticlimax was not a disappointment but a lesson. The quiet outcome revealed subtleties that could only be appreciated by careful observation: how resilient objects behave near supermassive black holes, how envelopes of gas interact with intense gravitational fields, and how minor differences in density can drastically alter the fate of a cosmic object. In many ways, the lack of fireworks was a clue, guiding scientists toward the deeper mystery of G2's survival and internal structure. Even in hindsight, this anticlimactic moment was transformative. It redefined expectations for how black holes interact with nearby material, showing that catastrophic destruction is not inevitable even under extreme tidal forces. The universe, as always, proved more subtle than human imagination had predicted. While no dramatic flare lit up the sky, G2's quiet endurance spoke volumes about the hidden resilience of some objects, and it left astronomers with one of the most intriguing puzzles of the decade. The G2 event, despite its anticlimactic visual display, turned out to be a watershed moment in our understanding of black holes, particularly how they interact with surrounding material. Before G2's approach, many of the models for accretion, the process by which black holes consume gas, dust, and other matter, relied heavily on theoretical calculations, simulations, and indirect observations. From distant active galactic nuclei, Sagittarius A, our Milky Way's supermassive black hole, was relatively quiet in comparison to these active galactic centers, and thus direct observations of its feeding behavior were limited. G2 presented a unique, near-field laboratory to test these theories. One major lesson from G2's passage was that the density and structure of the infalling object matters enormously. Previous models assumed that clouds of gas falling toward a black hole would be shredded almost entirely, with the material quickly joining the accretion flow. G2, however, demonstrated that if an object has a dense core or cohesive structure, much of its material can remain bound and avoid immediate accretion. This finding forced scientists to refine their assumptions about how gas interacts with a black hole's tidal field. It highlighted that not all matter near a supermassive black hole will feed it efficiently, and that the internal properties of the infalling object can dramatically alter the outcome. The event also provided insights into the temporal dynamics of accretion. Observations revealed that Sagittarius A did not flare significantly despite G2's close approach, suggesting that feeding a black hole is not as simple as throwing gas toward it. Material can be temporarily held in orbit around a dense object, or in some cases, it may be ejected back into space rather than falling inward. These subtleties helped astronomers understand that black hole accretion is a complex, often inefficient process influenced by the structure, velocity, and composition of surrounding matter. Another critical takeaway was the role of tidal forces and their limits. G2's survival illustrated that tidal forces, while immensely powerful, are not absolute determinants of destruction. The event showed that objects with sufficient internal cohesion, or those embedded with dense cores, can withstand encounters that would otherwise be catastrophic. This realization has prompted astrophysicists to rethink the outcomes of other near-black hole encounters and to incorporate more nuanced criteria for tidal disruption in their models. G2 also encouraged multi-wavelength observational strategies for studying black holes. The coordinated campaigns, combining infrared, X-ray, and radio observations, demonstrated the importance of looking at black hole interactions across the electromagnetic spectrum. Each wavelength revealed different aspects of the encounter. Infrared traced the cloud structure and heating, X-rays indicated high-energy interactions, or their absence, and radio waves mapped potential shockwaves and ionized gas. This holistic approach has since influenced observational strategies for other black holes, particularly in studying transient events and near-periapse interactions. Beyond the immediate mechanics of accretion, the event highlighted the importance of long-term monitoring. G2's journey and post-encounter observations revealed that black hole interactions can evolve slowly and unpredictably, and that a single snapshot is rarely sufficient to understand these processes. Astronomers realized that tracking objects over years or decades near supermassive black holes can provide critical data about orbital dynamics, tidal effects, and delayed accretion events. Finally, G2 challenged assumptions about population dynamics near black holes. Its survival and the possible existence of other G-type objects near Sagittarius A suggested that the galactic center may host a previously underestimated number of dense, resilient objects, including stellar merger remnants, cloaked stars, or unusual compact clouds. This has implications for understanding the evolution of stars in dense galactic environments and the role of black holes in shaping the surrounding stellar population. In essence, G2's passage served as both a test and a revelation. It demonstrated the limits of existing models, prompted revisions in our understanding of tidal forces and accretion efficiency, and emphasized the importance of combining observational data with flexible theoretical frameworks. The event underscored that black holes, while powerful, are not always the predictable destroyers they are often imagined to be. Their interactions with nearby matter are more complex, contingent, and nuanced than previously believed. G2 provided astronomers with a rare, near-field case study of black hole physics in action, a cosmic laboratory that will continue to influence theories of accretion, stellar dynamics, and the evolution of galactic centers for decades to come. The trajectory of G2 around Sagittarius A is one of the most fascinating aspects of this enigmatic object. Its orbit is highly elliptical, bringing it perilously close to the supermassive black hole at the center of the Milky Way before swinging back out into a much wider arc. This path, called a highly eccentric orbit, has allowed astronomers to study both the dynamics of G2 itself and the gravitational influence of Sagittarius A in exquisite detail. Tracking G2's movements has become a cornerstone of understanding the complex interplay between dense objects, diffuse material, and black hole gravity in the galactic center. G2's orbit was initially determined through years of careful observation using some of the most advanced telescopes in the world. Infrared observations were particularly important, as the galactic center is obscured by thick clouds of interstellar dust that block visible light. Instruments such as the Very Large Telescope, VLT, in Chile and the Keck Observatory in Hawaii have been critical in this effort. By capturing repeated high-resolution images over months and years, astronomers were able to trace the position of G2 against the backdrop of surrounding stars, measuring not only its location but also its velocity and acceleration as it moved under Sagittarius A's gravitational influence. The cloud's orbital parameters revealed an astonishingly close periapse, the point at which it comes nearest to the black hole, estimated to be only a few hundred astronomical units away, roughly 0.03 light-years. At this distance, the tidal forces from Sagittarius A are extremely strong, which is why G2 survival was so shocking. Its aphelion, or farthest point from the black hole, stretches out many times farther, giving the orbit its highly elongated shape. This kind of extreme ellipticity is not uncommon in the galactic center, where interactions with other stars and dense objects can nudge bodies into elongated trajectories over time. Tracking G2's orbit requires not just positional measurements but also spectroscopy. By analyzing the Doppler shift of light emitted by G2's gas, astronomers can determine how fast it is moving toward or away from Earth. These velocity measurements, combined with spatial imaging, allow for precise reconstruction of its three-dimensional orbit around Sagittarius A. Over time, this data has revealed subtle changes in G2's motion, including slight elongation of its gas envelope and minor deviations caused by tidal interactions. The orbit itself provides crucial insights into the forces at play. The very shape of G2's path reflects the gravitational dominance of Sagittarius A, but also hints at the cloud's internal structure. If G2 were a simple gas cloud, tidal forces during periapse would have significantly altered its trajectory due to mass loss. That the orbit remained largely predictable and coherent supports the theories that G2 possesses a dense core, whether a star or a merged stellar remnant. Essentially, its orbital behavior acts as a dynamical signature of its hidden resilience. Beyond its individual significance, G2's orbit also serves as a natural probe of the galactic center. By tracking how it moves through the intense gravitational field of Sagittarius A, astronomers can refine estimates of the black hole's mass and study the distribution of other material in the region. Each precise measurement adds another piece to the puzzle of how stars, gas clouds, and other exotic objects interact in one of the densest and most dynamic environments in the galaxy. Long-term monitoring of G2's orbit also raises intriguing possibilities for the future. As it continues along its eccentric path, it may pass closer to other stars, clouds, or remnants, potentially experiencing additional tidal interactions. Its motion could reveal further hidden structures within the cloud, or changes in the orbit could hint at gravitational influences from unseen objects near Sagittarius A. In other words, following G2 isn't just about understanding one object, it's about using it as a probe to map and explore the galactic center's invisible forces. In short, G2's orbit is both extraordinary and highly instructive. Its highly elongated path brought it close enough to one of the universe's most destructive forces to test its resilience, and careful tracking has allowed astronomers to uncover subtle details about its nature, the black hole's gravity, and the surrounding environment. The orbit turns G2 into a moving laboratory, offering a dynamic perspective on the extreme physics of the Milky Way's heart. One of the most remarkable features of the G2 cloud is its infrared glow, which has been essential for studying it against the densely obscured backdrop of the Milky Way center. Unlike visible light, which is easily blocked or scattered by dust and gas, infrared radiation can penetrate the thick clouds of interstellar material that dominate the galactic core. This property has allowed astronomers to detect, track, and analyze G2 in ways that would have been impossible using optical telescopes alone. G2's infrared emissions arise primarily from the heating of its gas and dust. If G2 contains a dense core, a star, a merged stellar remnant, or some other compact object, then the core's energy contributes significantly to heating the surrounding envelope. Even a relatively faint object, when wrapped in a layer of gas and dust, can emit enough infrared light to make the cloud observable from tens of thousands of light-years away. Essentially, the cloud behaves like a glowing lantern cloaked in fog. The light escapes in infrared wavelengths, providing astronomers with a clear signal amidst the cosmic dust. Observatories such as the Very Large Telescope, VLT, in Chile, the Keck Observatory in Hawaii, and space-based instruments like the Spitzer Space Telescope have played a crucial role in detecting and monitoring this glow. By measuring the infrared brightness and distribution across G2, astronomers can infer the cloud's size, shape, and temperature. These measurements also allow scientists to detect subtle changes over time, such as elongation caused by tidal forces or potential brightening if the cloud interacts more closely with surrounding material near Sagittarius A. The infrared glow has been especially important in tracking G2's orbital motion. In visible light, the dense dust and gas near the galactic center would obscure nearly everything, making G2 essentially invisible. Infrared observations, however, allow telescopes to see through the dust, tracing the cloud's path and revealing how it stretches, distorts, or maintains its structure as it approaches the black hole. This capability has been fundamental to understanding both the dynamics of G2 itself and the gravitational influence of Sagittarius A on nearby objects. Beyond simple detection, the infrared glow. provides clues to G2's internal structure. For example, a diffuse gas cloud without a dense core would cool more quickly and dim as it approached the black hole. The fact that G2 maintained a detectable infrared luminosity even at periaps suggests that some internal source, likely a star or compact object, was heating the surrounding material, sustaining the glow. The infrared signature is therefore not just a tool for observation. It is also evidence supporting the dense core and binary merger theories. Infrared observations also help astronomers understand the composition and density of the cloud. By examining the spectrum of the emitted light, scientists can detect the presence of specific molecules, dust grains, and ionized gases. This spectral analysis allows them to estimate how much mass is concentrated in the outer envelope versus the potential hidden core. In other words, the infrared glow provides a window into both the physical and chemical structure of G2, revealing details that are otherwise inaccessible. In addition, monitoring G2 in infrared over time has created a continuous record of its evolution. As the cloud swings around Sagittarius A, astronomers can compare images taken months or years apart, tracking subtle elongations, shifts in brightness, or changes in the distribution of material. These observations allow scientists to test models of tidal interactions, accretion processes, and cloud dynamics in extreme environments. The glowing cloud thus becomes a living experiment in high-energy astrophysics, visible only because of its infrared emission. In short, G2's infrared glow is more than just a spectacular feature. It is the key that has allowed astronomers to study one of the most mysterious and resilient objects in our galaxy. Without it, G2 would likely have remained undetected, hidden in the galactic center's dense dust. Instead, the infrared light provides not only a roadmap of the cloud's orbit but also critical clues about its nature, composition, and the hidden forces that allow it to survive near the Milky Way's supermassive black hole. The G2 cloud has sparked one of the most intriguing debates in modern astronomy. What exactly is it? Despite years of observation, modeling, and analysis, there is no unanimous answer. The question seems deceptively simple. On the surface, G2 appears to be a glowing cloud of gas orbiting Sagittarius A, but the closer scientists examine it, the more mysterious it becomes. Its survival during periaps, infrared glow, and unusual orbital dynamics have fueled heated discussions, with experts divided over whether G2 is a gas cloud, a star cloaked in dust, a stellar merger remnant, or an entirely new type of object never before observed. The first camp of astronomers holds to the classical gas cloud interpretation. They argue that G2 is primarily a diffuse collection of hydrogen, helium, and interstellar dust. Early observations in 2011 suggested that it had no solid core, no compact mass at its center, and that it simply drifted through the galactic center as a fragile cloud. Proponents of this idea note that gas clouds are common in the Milky Way, particularly near the galactic center, where gravitational interactions and stellar winds constantly stir and redistribute material. From this perspective, G2 is unusual only in that it survived longer than expected, perhaps due to being slightly denser than average or slightly elongated in a way that minimized tidal stress. However, the second camp argues that G2 is more than a cloud. It is likely a star or a compact object cloaked in gas and dust. This view gained traction after the anticlimactic periaps in 2014 revealed that G2 had not been shredded by Sagittarius A's tidal forces. Supporters of this interpretation point to the infrared glow as evidence of an internal heat source, most plausibly a star, that sustains the surrounding gas envelope. From this perspective, G2 is not fragile at all. Its apparent vulnerability is deceptive. This camp also cites orbital stability. A simple gas cloud would have been more dramatically affected by the black hole's gravity, yet G2 maintained a predictable, coherent trajectory. The binary star merger theory, which forms another faction of the debate, offers an even more exotic explanation. In this model, G2 is the aftermath of two stars colliding and merging near the galactic center. The merged star would be surrounded by a thick envelope of gas and dust, creating the appearance of a diffuse cloud while concealing a dense, resilient core. Advocates of this theory argue that it reconciles several observations: the infrared luminosity, the resilience to tidal forces, and subtle changes in shape during periaps. According to this theory, G2 represents not just a single object but a rare and transient phase in stellar evolution, a hybrid form bridging gas clouds and stars. Adding to the complexity, a fourth, more speculative camp suggests that G2 might represent an entirely new class of object. These scientists note that none of the standard explanations perfectly account for all observations. For example, while the dense core models explain survival, they do not fully explain why G2's gas envelope appears relatively diffuse yet cohesive. Similarly, the binary merger model fits many details but predicts certain observational signatures that have yet to be confirmed. Some speculate that G2 could be a protostar shrouded in gas, an unusually bloated planetary object, or even a type of stellar remnant with properties not yet understood. These possibilities, while speculative, highlight how G2 continues to challenge the boundaries of current astrophysical theory. The debates are not just academic, they have real implications for how we understand the dynamics of the galactic center. If G2 is a simple gas cloud, its survival challenges our models of tidal disruption. If it is a star or merger remnant, it suggests that the galactic center may harbor many such resilient objects, affecting our understanding of stellar evolution, dynamics, and black hole feeding processes. And if it is something entirely new, it could point to phenomena in extreme environments that are entirely outside our current framework. Adding to the discussion are subtle observational details. Spectroscopic studies, which examine the light emitted at different wavelengths, have revealed variations in temperature, velocity, and density within G2. These variations can be interpreted in multiple ways depending on which theory one favors, fueling further debate. Similarly, the lack of dramatic interaction with Sagittarius A's accretion disk raises questions about how gas and stars behave near supermassive black holes, a question central to understanding the evolution of galactic centers across the universe. Ultimately, the ongoing debates about G2 reflect both the limits of observation and the complexity of the galactic center. Each new observation can shift opinion slightly, and no single model fully captures every aspect of G2's behavior. What is clear, however, is that this object has forced astronomers to think creatively, challenge assumptions, and consider phenomena that might have been dismissed before. In this sense, G2 is not just a mystery, it is a catalyst, pushing the boundaries of astrophysics and inspiring scientists to refine their understanding of the universe's most extreme environments. G2's resilience becomes even more remarkable when compared to typical gas clouds in the galaxy. Most interstellar gas clouds are fragile by nature, loosely bound collections of hydrogen, helium, and dust, held together primarily by their own weak gravity and internal pressure. These clouds drift through space, often shaped and disrupted by stellar winds, supernova, explosions, or the tidal forces of nearby massive objects. A typical cloud, if it were to approach a supermassive black hole like Sagittarius A, would be shredded almost instantly, stretched into long filaments, and partially or entirely accreted. It would not survive the encounter, and its identity as a coherent structure would vanish. Normal gas clouds also behave predictably when observed in the infrared. Their luminosity tends to vary according to density and temperature changes, but without an internal heat source, they cannot sustain significant emissions over time. As they encounter external forces, whether gravitational or radiative, they disperse quickly, losing both mass and structure. In contrast, G2 maintained a detectable infrared glow throughout its journey, signaling an internal energy source, most likely a hidden star or a dense core. This ability to retain heat and coherence is a striking divergence from the behavior of ordinary gas clouds. Furthermore, normal gas clouds are heavily influenced by tidal forces in the gravitational field of a massive object. The difference in gravitational pull between their near and far sides causes them to stretch and elongate, often breaking them apart before they can make a close approach. G2 defied this expectation. While some elongation was observed, the object did not fragment. Its survival suggests that there is a stabilizing mechanism at work, whether it is a stellar core, a merger remnant, or some other form of compact mass embedded within the envelope. This sets G2 apart as unusually robust, capable of withstanding forces that would obliterate typical clouds. Another contrast is seen in orbital behavior. Most gas clouds near the galactic center are susceptible to perturbations from surrounding stars, black holes, and dense gas streams. Their paths can be erratic, and they often lose coherence after close encounters. G2's orbit, however, remained highly predictable and stable, despite its close approach to Sagittarius A. This stability is another indicator that it is not a simple cloud, and it distinguishes G2 from the majority of interstellar gas clouds observed elsewhere in the galaxy. The comparison also extends to size and density. While G2 is not enormously massive by cosmic standards, it is dense enough to resist tidal disruption, whereas ordinary clouds of similar size would be torn apart. Its envelope, though extended, does not behave like the loosely bound hydrogen clouds commonly found in star-forming regions or the diffuse molecular clouds scattered throughout the Milky Way. In many ways, G2 straddles the line between a gas cloud and a stellar object, a hybrid that is rare and unusual. Even when considering clouds that orbit black holes in other galaxies, G2 remains exceptional. Most known accretion events involve dense clumps of gas being consumed, producing observable flares and energetic outbursts. G2, on the other hand, barely contributed to Sagittarius A's accretion activity, indicating that its structure allowed it to survive rather than be absorbed. Its resilience, therefore, is not only unusual for Milky Way gas clouds but also unique among the limited examples of objects that have been observed near supermassive black holes elsewhere. In essence, the comparison highlights just how extraordinary G2 is. Normal gas clouds are fragile, ephemeral, and easily destroyed by gravitational extremes. G2, by contrast, is unusually coherent, infrared bright, and resilient. Its survival challenges our understanding of how objects interact with supermassive black holes and forces us to reconsider the boundaries between diffuse clouds and compact stellar objects. Where ordinary clouds fail, G2 persists, earning its reputation as a cosmic anomaly, and one of the most resilient objects ever observed in the heart of a galaxy. Studying G2 matters not just because it is a mysterious and resilient object, but because it provides a window into the extreme physics of the universe, particularly the intense environment surrounding supermassive black holes. Sagittarius A, while relatively quiet compared to active galactic nuclei, represents one of the most extreme gravitational regions in our galaxy. Understanding how matter behaves in such an environment is essential for refining astrophysical theories, and G2 offers a rare, tangible probe into these dynamics. One of the primary reasons G2 is so valuable is that it allows scientists to observe tidal forces in action. The tidal forces near a supermassive black hole are immense, stretching and distorting objects that venture too close. Most stars and gas clouds would be torn apart before anyone could study them in detail. G2, however, survived its perilous encounter, allowing astronomers to examine both its deformation and its resilience. By comparing observational data with theoretical models, scientists can better understand how gravity operates under extreme conditions, including the limits of tidal disruption and the role of internal structure in survival. G2 also provides a unique opportunity to study accretion physics in real time. Accretion, the process by which black holes consume surrounding matter, is a fundamental mechanism in astrophysics. It powers quasars, drives jet formation, and governs the growth of supermassive black holes over cosmic time. Prior to G2, most accretion studies relied on indirect observations or simulations. G2's passage offered a real-time experiment. How does a dense or partially diffuse object interact with a black hole's gravitational field, and what fraction of its mass is ultimately captured? The fact that Sagittarius A did not flare dramatically teaches us that accretion is not always efficient and that some material can survive even close encounters. These insights refine our models of black hole feeding across the universe. Beyond accretion, G2's behavior informs our understanding of stellar evolution in extreme environments. If G2 contains a star or is the remnant of a stellar merger, its survival suggests that stars can not only exist but adapt in the hostile environment near a supermassive black hole. This challenges previous assumptions that such environments are purely destructive and opens up questions about how stars form, evolve, and interact in dense galactic centers. Studying G2 can help astronomers answer questions like, how common are stars or compact remnants near black holes? Can mergers or collisions in such regions produce unusual or hybrid objects? Additionally, G2's orbit and dynamics provide a tool to measure the gravitational potential of the galactic center. By tracking its motion with high precision over years, astronomers can calculate the mass of Sagittarius A and map how gravity is distributed in its vicinity. Such measurements are essential for testing predictions of general relativity in strong gravitational fields, where spacetime curvature is extreme. G2's passage, therefore, is not just a curiosity. It is a direct probe into the fabric of spacetime itself. Another reason G2 matters is its ability to challenge and expand theoretical models. Prior to its observation, simulations predicted its destruction and the likelihood of bright flares. Its survival contradicted these models, forcing scientists to revisit assumptions about cloud density, internal cohesion, and the nature of tidal interactions. By confronting theory with real data, G2 has driven progress in astrophysics, highlighting the importance of observational evidence in shaping our understanding of high-energy phenomena. Finally, G2 has broader implications for the study of galactic nuclei across the universe. Supermassive black holes are central to the evolution of galaxies, regulating star formation and influencing galactic structure. Understanding the behavior of objects like G2 helps astronomers predict how matter behaves in similar regions elsewhere, including in galaxies too distant to study in comparable detail. It provides a benchmark, a rare local example, for processes that are otherwise inferred from faraway galaxies. In short, studying G2 matters because it bridges theory and observation in one of the most extreme corners of the cosmos. It teaches us about tidal forces, accretion efficiency, stellar evolution, gravitational potential, and the limits of our theoretical models. In doing so, it helps astronomers unlock the physics governing not just our own galactic center, but potentially the behavior of black holes and surrounding matter across the universe. G2 is more than a cloud or a star. It is a natural laboratory, offering a rare chance to witness extreme physics in action. The G2 cloud's journey around Sagittarius A is unlikely to be a one-off event in the dynamic environment of the Milky Way's galactic center. The discovery of G2 has sparked discussions about the possibility that other similar objects, dense gas clouds, cloaked stars, or stellar merger remnants, may also traverse paths that bring them perilously close to the supermassive black hole. The galactic center is not empty. It is a bustling, chaotic environment, filled with stars, stellar remnants, gas streams, dust clouds, and other exotic objects, all interacting under the influence of extreme gravity. In such a densely packed region, encounters with the black hole are inevitable over cosmic timescales. Astronomers suspect that G2 may not be unique. Observations over the past decades have revealed multiple gas clouds and compact objects orbiting Sagittarius A, though most are smaller, less luminous, or harder to detect. Many of these objects are likely remnants of past stellar interactions, collisions, or tidal disruptions. Some may be loosely bound gas clouds like G2, while others could be cloaked stars or exotic merger products. The key takeaway is that the galactic center is a dynamic system, and G2 represents just one example of a class of objects that can survive, or at least partially survive, close encounters with a supermassive black hole. Predicting future encounters requires careful tracking of known objects and modeling of the orbital dynamics in the galactic center. Many stars orbit Sagittarius A on highly elliptical paths, and interactions among stars can scatter gas clouds into new trajectories. Gas streams and diffuse clouds may gradually be nudged inward by gravitational interactions, potentially creating future G2-like events. When these objects approach the black hole, astronomers can study tidal effects, accretion dynamics, and the interplay of stellar or gas envelopes with extreme gravity, essentially repeating and expanding the lessons learned from G2. The possibility of future encounters also opens the door to long-term monitoring campaigns. Facilities like the Very Large Telescope, VLT, Keck Observatory, and space-based infrared telescopes are already scanning the central parsec of the Milky Way for faint, fast-moving objects. Each detection represents an opportunity to witness the gravitational ballet around a supermassive black hole in real time. In addition, next-generation observatories, such as the James Webb Space Telescope, are capable of detecting even fainter infrared emissions, increasing the likelihood of discovering more G2-like objects. The implications of repeated encounters are profound. If multiple dense gas clouds or stellar remnants repeatedly interact with Sagittarius A, this could influence the long-term evolution of the black hole's accretion disk, affect star formation rates in the central parsec, and even contribute to the overall dynamics of the inner galactic region. Each object that survives or is partially destroyed provides new data on the limits of tidal disruption, the resilience of complex stellar systems, and the behavior of matter in extreme gravity. Moreover, future encounters could refine our understanding of stellar population dynamics in extreme environments. The fact that G2 survives suggests that similar resilient objects could exist in greater numbers than previously thought. If more G2-like clouds or merger remnants are discovered, astronomers would gain insight into how stars evolve in close proximity to supermassive black holes, how binary interactions and mergers occur under such extreme gravitational stress, and how these processes influence the population of stars and remnants in the galactic core. Finally, G2 has set a precedent for predictive astronomy. By understanding its orbit and properties, scientists can develop models for identifying potential future encounters before they occur. This predictive capability allows the astronomical community to prepare for observations in advance, potentially catching the next G2 in real time and observing interactions that may include tidal stretching, partial accretion, or even unexpected phenomena. Each successive encounter has the potential to refine our theories and provide an ever clearer picture of the extreme physics at play near supermassive black holes. In short, G2 is not just an isolated anomaly. It is a harbinger of a broader class of objects navigating the dangerous gravitational environment near Sagittarius A. The possibility of other similar objects crossing paths with the black hole offers the promise of future discoveries, providing repeated opportunities to study survival, tidal interactions, and accretion processes in ways that were previously thought to be impossible. The Galactic Center is a dynamic laboratory, and G2 may be just the first of many lessons waiting to be revealed. The G2 cloud provides a rare glimpse into the complex and extreme processes of stellar evolution in the vicinity of a supermassive black hole, an environment that is radically different from the more tranquil regions of a galaxy where most stars form and evolve. Near Sagittarius A, gravity is intense, stellar densities are high, and interactions between stars, gas clouds, and compact objects occur frequently. Studying G2 structure, trajectory, and survival offers valuable insights into how stars might form, merge, or ultimately meet their end in such extreme conditions. If G2 indeed contains a dense core or is the product of a binary star merger, it underscores the idea that stars can undergo unusual evolutionary pathways near black holes. In typical galactic environments, stars form from molecular clouds, evolve over millions or billions of years, and eventually die through processes such as supernovae, planetary nebula formation, or quiet collapse into white dwarfs. But near a supermassive black hole, the story becomes more chaotic. Gravitational interactions with the black hole and nearby stars can perturb stellar orbits, increasing the likelihood of collisions, mergers, or tidal stripping. G2 could represent a stellar object caught in this extreme milieu, possibly a merged star that has been shrouded in gas and dust as a result of its violent formation. The binary star merger theory for G2 is particularly enlightening. Mergers can produce unusually luminous, bloated stars with envelopes that survive extreme tidal forces, creating transient objects that appear as hybrid gas star systems. Studying G2's properties provides astronomers with observational data on such processes in action. By examining its infrared emissions, orbital stability, and resilience to tidal forces, scientists can better understand the physics of mergers. Near black holes, including energy dissipation, mass redistribution, and envelope dynamics. These insights have broad implications for the population of stars in galactic centers, suggesting that unusual stellar objects may be more common than previously thought. G2 also informs theories about star formation under extreme tidal stress. The galactic center is rich in gas and dust, but the strong gravitational field can inhibit standard star formation processes. Objects like G2 may represent rare pockets where dense material is able to coalesce into stars despite these challenges, or remnants of stars that have been partially stripped and reshaped by the black hole's gravity. Observing G2 allows astronomers to explore how dense cores survive, how gas envelopes respond to extreme tidal forces, and how these processes might influence stellar birth and evolution in high-density, high-gravity regions. Furthermore, G2 survival challenges assumptions about stellar death in extreme environments. A fragile gas cloud should have been destroyed by the tidal forces of Sagittarius A, yet G2 persisted. If it contains a stellar core, this resilience demonstrates that stars or stellar remnants can endure conditions previously thought to be fatal. Understanding how this is possible could refine models of stellar lifespans, particularly for stars that exist in close proximity to supermassive black holes. It may also shed light on the fate of other unusual objects observed near galactic centers, such as compact binaries, extreme blue stragglers, or hypervelocity stars that have survived violent interactions. G2 also acts as a case study for the interplay between gas and stars in dense environments. Its envelope of gas and dust may have originated from stellar outflows, merger ejecta, or residual material from its formation. Observing how this envelope behaves under extreme gravity provides insights into how stars exchange mass with their surroundings, how gas envelopes can shield cores from destruction, and how such processes influence stellar evolution in dense clusters near black holes. In essence, G2 allows scientists to observe the ongoing dialogue between stellar matter and the forces of a supermassive black hole. Finally, the study of G2 informs population models for galactic centers. By understanding how objects like G2 form, survive, and evolve, astronomers can estimate the frequency of similar resilient stars or gas-star hybrids. This has implications for predicting stellar densities, merger rates, and even the rate at which black holes accrete mass in their central parsecs. G2 provides a rare observational anchor for these models, connecting theoretical predictions with real, measurable phenomena. In summary, G2 is more than an isolated curiosity. It is a laboratory for extreme stellar evolution. By examining its structure, survival, and interactions with Sagittarius A, astronomers gain insights into how stars can form, merge, and endure in environments dominated by supermassive black holes. G2 highlights the diversity of stellar pathways, demonstrating that even in the galaxy's most hostile regions, stars and stellar remnants can exist, adapt, and sometimes thrive. It challenges conventional wisdom about stellar fragility and illuminates processes that are otherwise invisible, deepening our understanding of the complex life cycles of stars in the heart of galaxies. The survival of G2 near Sagittarius A embodies a profound lesson about the resilience of objects in the universe, particularly in the face of forces that seem insurmountable. At first glance, G2 appears fragile, a luminous envelope of gas, seemingly vulnerable to the immense tidal forces of a supermassive black hole. Yet its endurance challenges this perception, making it a symbol not just of scientific curiosity, but of cosmic resilience itself. Its ability to withstand conditions that would obliterate ordinary objects elevates it from an astronomical anomaly to a representation of survival under extreme stress. Cosmic destruction operates on scales that dwarf human comprehension. Supermassive black holes, like Sagittarius A, exert gravitational forces so powerful that even light cannot escape. Tidal forces near their event horizon stretch and distort matter, tearing stars, clouds, and sometimes entire planetary systems apart. The natural expectation was that G2 would follow the same fate. Yet, against these odds, it persisted, maintaining its integrity, luminosity, and trajectory. In doing so, G2 demonstrates that strength in the universe does not always manifest as mass or density alone, but can also reside in structure, cohesion, and the hidden properties of matter. This strength of mystery is not merely physical, it is also conceptual. G2 reminds scientists that our understanding of the cosmos is still incomplete. Theories predicted destruction, yet observation revealed endurance. In this sense, G2 becomes a symbol of the unexpected, a reminder that even under conditions dominated by seemingly absolute laws of gravity and tidal disruption, the universe retains room for anomalies and surprises. Its survival forces astronomers to confront uncertainty, revise models, and expand the boundaries of what is considered possible. The cloud's endurance can also be seen metaphorically. Just as it resisted being torn apart by Sagittarius A's immense gravitational pull, G2's survival highlights how objects, even in extreme environments, can possess hidden resilience. If it contains a dense core or a stellar remnant, that internal strength becomes the anchor allowing the surrounding gas to withstand forces millions of times stronger than anything experienced on Earth. From a scientific perspective, this resilience provides critical insight into how certain structures in the universe, whether stars, merger remnants, or gas clouds, can persist in seemingly hostile conditions, offering clues about long-term survival strategies in high-gravity regimes. Moreover, G2's enigmatic nature fuels a sense of wonder that transcends its physical properties. Its resilience is not only a lesson in astrophysics but also a symbol of the universe's capacity for complexity and subtlety. In a cosmos often imagined as violent and destructive, G2 demonstrates that fragility can coexist with strength, and that endurance is possible even in the most extreme settings. Its survival challenges deterministic thinking and exemplifies how cosmic phenomena often defy expectations, prompting both humility and curiosity among those who study them. The mystery surrounding G2's strength also emphasizes the limits of human understanding in extreme astrophysics. The object has shown that standard models, those assuming simple tidal destruction of gas clouds, do not capture the full range of behaviors possible near supermassive black holes. G2 forces scientists to consider factors such as hidden cores, internal cohesion, and complex gas dynamics, illustrating that resilience can take forms that are not immediately obvious. Its persistence is a vivid reminder that the universe often operates in ways that elude straightforward prediction, requiring observation, patience, and ingenuity to unravel. Finally, G2 survival can be framed as a metaphor for the broader universe. Even in environments of extreme destruction, structures can endure, adapt, and persist. Whether it is a cloaked star, a merged stellar remnant, or an unusual hybrid object, G2 exemplifies how hidden strengths can preserve integrity against overwhelming forces, offering both scientific lessons and a poetic illustration of cosmic perseverance. Its continued existence encourages astronomers to seek out other unusual objects near Sagittarius A, reminding us that resilience may be more common in the universe than we currently recognize. In essence, the strength of mystery embodied by G2 is a dual phenomenon. It represents physical endurance against tidal destruction while simultaneously symbolizing the intellectual and observational resilience required to understand the universe. Its survival is both literal and figurative, a cosmic paradox that simultaneously challenges and inspires. By studying G2, scientists confront one of the most profound truths of astrophysics. The universe is full of objects that defy simple categorization, and even under conditions of extreme destruction, endurance and complexity can emerge. So, after exploring every astonishing detail about G2, from its discovery, orbit, and infrared glow to its survival against one of the most powerful forces in the galaxy, we are faced with a profound question: what is the strongest object in the universe? For decades, our instincts would have guided us towards supermassive black holes, neutron stars, or even entire galaxies. These are the cosmic titans, wielding gravitational forces, densities, and energies that defy comprehension. Yet G2 compels us to reconsider our assumptions. Strength, in this context, is not merely about raw mass, gravitational pull, or explosive power. It is about resilience, endurance, and the ability to withstand forces that should, by every expectation, obliterate an object. G2, a seemingly fragile cloud of gas and dust, demonstrates a type of strength that is not brute force but subtle durability. Unlike black holes, which consume everything in their path, or neutron stars, which withstand collapse due to quantum degeneracy pressure, G2 survived intact while skimming past Sagittarius A, enduring tidal forces that should have shredded it into molecular threads. Its strength is structural and adaptive, rooted in hidden properties that are invisible to casual observation. Perhaps a dense core, perhaps the remnants of a stellar merger, or some other mechanism yet to be fully understood. It is this hidden resilience that sets G2 apart as an extraordinary entity in our universe. Framing the question this way challenges conventional perspectives on what it means to be strong. Often, strength is equated with aggression, destruction, or dominance, the ability to overpower or consume. But G2 demonstrates that strength can also manifest as endurance in the face of overwhelming odds, a quiet persistence where destruction was expected. It survived in an environment where ordinary stars or gas clouds would have been obliterated, highlighting a quality of resilience that is both remarkable and rare. In a universe where chaos and destruction are ubiquitous, the ability to endure is perhaps the ultimate demonstration of strength. Moreover, G2 forces us to rethink the cosmic hierarchy of power. While a black hole dominates through gravitational might, it is G2 that demonstrates moral, or perhaps metaphorical, strength, the capacity to persist despite vulnerability. In this sense, the strongest object in the universe is not necessarily the one that consumes or destroys, but the one that can endure when faced with forces that could annihilate it. Its survival is a triumph of subtle physics, a testament to how structure, cohesion, and hidden complexity can confer strength in ways we might never expect. G2's story also reframes our understanding of cosmic resilience more broadly. The universe is full of destructive forces, supernovae, gamma-ray bursts, gravitational collisions, but it is also full of structures that survive, adapt, and evolve despite these dangers. G2 exemplifies this principle at the most extreme scale. A single object enduring the gravitational pull of a supermassive black hole. By surviving, G2 reminds us that resilience is as much a measure of strength as raw energy or mass. Finally, reframing the question in this way has profound implications for science and philosophy alike. It invites us to look beyond the obvious, to question assumptions about power and influence in the cosmos. It suggests that some of the universe's most remarkable phenomena may not be the ones we expected: exploding stars, colliding galaxies, or radiant quasars, but subtle objects whose hidden properties allow them to persist in extreme environments. G2 is a living example of this, a mysterious, enduring object that challenges our understanding, inspires our imagination, and redefines what it means to be strong in the universe. In conclusion, when we ask, once again, what is the strongest object in the universe? The answer might not be a black hole, a neutron star, or a galaxy. It might just be a mysterious gas cloud, G2, that survived the unthinkable, demonstrating that true strength can reside in endurance, hidden structure, and resilience against forces that defy comprehension. It teaches us that sometimes the universe's most powerful objects are not those that dominate or destroy, but those that endure when the odds are stacked impossibly against them. The story of the G2 cloud does not exist in isolation. It is part of a much bigger picture that speaks to one of the most humbling truths about the cosmos. The universe still hides surprises that challenge even our most advanced theories and models. For centuries, humanity has sought to understand the cosmos through observation, experimentation, and mathematics. And with every discovery, we have inched closer to unveiling its mysteries. Yet G2 reminds us, in spectacular fashion, that the universe is still full of puzzles, phenomena that defy predictions, and events that force us to rewrite our assumptions. Consider this. When G2 was first discovered in 2011, astronomers thought they knew what to expect. A fragile gas cloud, falling into the immense gravitational well of Sagittarius A, should have been shredded, consumed, and obliterated, providing a spectacular display of cosmic destruction. Instead, G2 endured, leaving scientists scratching their heads. This single anomaly was enough to upend established expectations about tidal forces, accretion, and the very definition of resilience near a supermassive black hole. If such a small object can defy our predictions, what else might the cosmos be hiding? This is where the broader theme emerges. G2 serves as a reminder that the universe is not a static machine that we can easily predict, but a dynamic and often surprising system, full of complexity and nuance. Every unexpected event, whether it is G2 survival, the discovery of fast radio bursts, or the detection of gravitational waves, forces us to confront the limitations of our knowledge and adapt. These surprises are not setbacks, they are the engine of scientific progress, showing us where our models fall short and where new physics may be waiting to be discovered. The survival of G2 also connects to the theme of cosmic diversity. Our universe is vast, containing not only billions of galaxies, stars, and planets, but also strange hybrids, oddities, and transitional objects that do not fit neatly into categories. G2 might be a cloaked star, a stellar merger remnant, or something entirely unprecedented. Whatever it is, it teaches us that nature does not conform to the tidy definitions we prefer. Instead, it produces a spectrum of objects that blur the boundaries between stars and clouds, between stability and destruction, between fragility and resilience. These edge cases expand our understanding and remind us that the universe often operates in the gray zones, not the black and white categories of textbooks. On a deeper level, G2 embodies the humility of science. Even with our most advanced telescopes, simulations, and theories, the cosmos continues to surprise us. The fact that something as seemingly fragile as a gas cloud can outwit the tidal forces of a black hole shows that our grip on cosmic truths is always provisional. This humility is not a weakness, it is the essence of science. Each time the universe surprises us, it hands us an opportunity to learn more, refine our models, and expand the horizons of human understanding. Moreover, G2's story highlights the importance of curiosity-driven exploration. When it was first observed, many astronomers rushed to point their telescopes at it, anticipating a fireworks display. Instead, they got something subtler but arguably more valuable, a mystery. And rather than dismissing the anticlimax, they embraced it, asking deeper questions and proposing new theories. This attitude, the willingness to let the universe surprise us and to follow those surprises wherever they lead, is the key to unlocking future discoveries, whether about black holes, dark matter, dark energy, or other cosmic puzzles yet unknown. Finally, G2 is a reminder that the universe is not just a stage of destruction and chaos, but also of endurance and unexpected resilience. For every supernova that obliterates a star, there is an object like G2 that resists destruction. For every black hole devouring matter, there are anomalies that escape or endure. This interplay of destruction and survival, chaos and order, is what makes the cosmos endlessly fascinating and profoundly mysterious. In the bigger picture, G2 is not just a single gas cloud near Sagittarius A, it is a symbol of the cosmos itself, unpredictable, surprising, and full of lessons waiting to be uncovered. It reminds us that we are still students of the universe, not its masters, and that even the smallest anomalies can reshape our understanding of reality. G2's endurance tells us that the story of the cosmos is far from finished, and that the greatest surprises may still lie ahead. As we reach the conclusion of G2's incredible story, it's worth reflecting on one of the most tantalizing aspects. G2 may not be alone. Its survival near Sagittarius A hints at a population of strange, resilient objects lurking in the galactic center. Objects that have somehow withstood forces powerful enough to obliterate ordinary stars and clouds. If G2 can survive, perhaps other cloaked stars, stellar merger remnants, or hybrid gas cloud objects are waiting to be discovered, quietly orbiting the supermassive black hole and challenging our understanding of what is possible in such extreme environments. Astronomers have already begun searching for similar phenomena. Using infrared and high-resolution imaging, they scan the crowded, dusty heart of the Milky Way, looking for faint, unusual objects with peculiar orbits. Some of these candidates may appear ordinary at first glance, but just like G2, a closer study could reveal hidden cores, unusual compositions, or other characteristics that defy expectation. Each discovery has the potential to rewrite what we know about the physics of extreme gravity, the dynamics of stellar evolution near supermassive black holes, and the diversity of cosmic structures that can exist in high-risk environments. The galactic center is a chaotic laboratory, teeming with stars, gas, and debris, all moving under the immense gravitational influence of Sagittarius A. In this environment, encounters like G2's are inevitable. Over time, more clouds or stellar remnants may drift close enough to provide scientists with opportunities to observe tidal interactions, accretion, and perhaps even new forms of survival. G2's story is therefore not just a singular event but the opening chapter of a continuing saga, one that could reveal an entire population of cosmic survivors. For enthusiasts and astronomers alike, this is an invitation to expect the unexpected. If a seemingly fragile cloud could endure where destruction seemed inevitable, what other anomalies might exist in the Milky Way's heart? Could there be more G-type objects hiding dense cores, waiting for their moment to test the limits of physics near a supermassive black hole? Could entirely new types of objects, never before imagined, be orbiting Sagittarius A, silently challenging our models of resilience and survival in extreme conditions? The takeaway is exhilarating. The universe continues to surprise us. G2 has already shifted our understanding of tidal forces, black hole interactions, and the resilience of cosmic objects. But it may just be the first of many revelations hidden in the galaxy's core. Every year, new observations, better telescopes, and more precise instruments increase the chances of finding another G2. A survivor whose journey will teach us even more about the extraordinary physics at play in the most extreme environments imaginable. So, while G2 has captured our attention as perhaps the strongest object in the universe, its story also sets the stage for future discoveries. The galactic center remains a frontier, a place where anomalies like G2 challenge assumptions, ignite curiosity, and hint at a universe far stranger and more resilient than we ever imagined. The cosmic stage is set, and the next chapter of extraordinary survival may be unfolding even as we watch. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.